ちょっと私の方で試しにやってみますね。Google ドックに置いて、ちょっとシェアすることにします。あ、でもそうか。コンパイルができないんだよね。Google ドックに置いても。700用にコンパイル、メイクファイル作っちゃったから。Webpack とかもリンクしなきゃいけないし。
なんで Python の方しか、Python の方、C はちょっと難しいかもしれない。
あと2分か。ちょっと私もちょっと少しだけ休憩させてもらおう。そうか。これを直してもらおうか。1週間直してもらおうか。So, everyone, I'd like to restart the module 3, the second whole session. I'm very sorry. I couldn't provide you the convenience of computational environment. It's really very sorry. Who cannot access or who cannot use our X700 server. But you see, okay, so this slide, so I already negotiated the system administrator to extend your account. This morning, he mentioned that it is until the so next week, the 15th of July, but today's some difficulty to their considering some difficulty to access the system, and of course someone there is not yet to register your password, so that the public key on the server. So I will again negotiate to extend the system. I don't know your ID availability. So probably one more week. So I will announce to you the exact date. But you can access until at least the 15th, so next week. So don't worry. If you cannot access the FX server today, so you can access tomorrow, the day after tomorrow. Yeah, you can do the exercise by yourself. So you can access the my document and the exercise code after this today's module 3. Yeah, please don't worry that. Okay, so going back to the slide to the some. Okay, so page. This is 40. Okay, so we did the submission of the we did the submission of our target binary code to the FX system. But we have not yet confirmed the result. So this is just results. So example of the results when you submit. When I submit it on my show, you will get very similar results. Of course, you rerun the same object. So okay. So first line. So this is the computational time to do the area decomposition with a double precision format, double precision accuracy. It takes okay, so I should enlarge. Okay, approximately the 4 second, including the backward, forward and backward the substitution. Yeah, so whole process to solve this linear system. On the other hand, so the single precision, so every factorization and the forward backward substitution, it took roughly the half of this double precision, or 2 seconds. So the computation results are as we expected. So double precision needs the double time compared to the single precision. And that's okay. So second value. So these are indicating the obtain the results, their accuracy, the precision more. So compared to these values, okay, that precision, yeah, it shows a good accuracy, 10 to the minus 12. But this means almost 12 digits are very, very reliable. So from the first digit to 12 digits, so this is correct. These are correct. Okay, so but as half a single precision, okay, you see 2.5 to minus 3. So always the 3 digits are correct. So there are the 9 digits difference, the big gap. So doing the iterative refinement, so we improved the accuracy. So approximately it's similar or the equivalent to the also double precision accuracy. So first iteration, second iteration, almost about 5 or 6. So it converges to almost the upper limit. So 1.1 or 10 to minus 11. So almost 11 digits are correct. Well, in the case the double precision, 12 digits, or mixed precision, iterative refinement, so 11 digits are correct. So just only the difference of the final digit. So this is very acceptable, the accuracy. So we reduce the computation time. So you can see that's a 2.73 seconds or so required to do the first step that you decomposition of single precision. And also 1, 2, 3, 4, 5, 8 iteration. Just only with this additionally 0.5 the half second. So compared to the precision, so it needs approximately the 4 seconds. Yes, we successfully reduce the computation time. Yeah, almost the same accuracy. Yeah, and we don't have to pay the electricity. Yeah, if you need this every time, we have to pay the $100 is expensive. So okay, the $5 for the single shot job. But this case, we eliminate the computation time. So just approximately 25%. So we have a payback from the the computer center. So every time, $2.5 payback. Yeah, it is a very, very reasonable and green. Yeah. Okay, so if you understand, or if you learn this kind of this type of the optimization technique, this is not only applicable to the linear system. The idea is extended to the other linear algebra method, computational method. But the typical or the standard one is the linear solver. So please learn this reminders of the RT requirement is a very, very powerful tool. So the accuracy is improved. Okay, so again, so your account is available at least next week, but I will negotiate the extension 1 or 2 more weeks, considering the situation, today's situation. Okay, so if you have some comments or some the claim to the accessibility to access of my center, so please send us or write down to the chat window. So I will send to my center system administrator. So that is a good experience for us. Okay, so if you have also no question, do you have any question to this this mixed precision issue or the linear algebra or high performance computing? Yes, and most of the communications are whether it's logging, so I can log in, I cannot still log in. But for the technical issue, if you have any question. Okay, so during the second half, so yeah, I will accept your questions. Okay, so we don't have enough time, so for the next, so I'd like to move to the second half. It's the very beginning of the neural network. Because the neural network has a common issue with the matrix computation. So matrix very fast, complex matrix modification. So I chose this topic, and I believe some guy from the Europe computer center, so they will teach you some aspect from the artificial intelligence or your network the applications. But my talk is just focused or emphasize that the principle of this neural network. Why or the how we utilize, take advantage of this neural network or the AI. So first question is, what do you image the artificial intelligence or the deep machine learning? Honestly, I'm not the AI guys. So in the beginning of this module, so I introduced my research topic or my expertise field is linear algebra high performance computing. So now I'm expert. But also I know there's the principle of this internal of this neural network, the deep neural network. So what do you imagine? Yeah, this is a good question. Yeah, please keep this answer to yes. But anyway, so because I'm not the expert for the AI, so I rely. So most of the my slides, so it's about on the textbook. So do you know fundamental of deep learning, so designing the next generation machine. This is a very good textbook to understand the principle of the new deep neural network. Of course, this is a very, very good principle. This is not application users. So this is a very good book for who wants to understand, or who wants to learn the neural network. So if you want to use a deep neural network or the toolkits that is already distributed or as open source. So please refer to the other some URL or the textbook or that some tutorials, manuals, which is already published on the internet. Okay, today my talk is very, very beginning. Okay. So AI, artificial intelligence. So this is sort of a good keyword, but also here, so it is equivalent to the intelligence machine, just a machine, machinery. This is also not the human and also the animal. So there is a question: can we emulate the human brain on our computer system? But that is a very big motivation to start for the AI, artificial intelligence. So yeah, so it is a scientific fiction or the movie and novels. So many robots, the computer, so they are speak or even or if so it has some humanity or something. But it is a machine or the program. So the motivation is, yes, we want to emulate it. The brain is, but yes, something intelligently makes something. So dream of the building an intelligent machine with brains like ourselves is, yes, it's a very, very big, sorry, it's a big dream. So, but we have to develop rapidly different programming on the computer. So using the techniques largely developed over the past decade. Several, okay, so 10 years or 20 years. So there were other approach to develop to emulate the artificial intelligence by list up the sort of very low or the, some programming segment to combine the sort of one program as a sort of human brain. But there were no successful result. So now we have another approach. So the typical difficulty is hidden in the some limitation in the traditional way to build the program on the sort of modern computer system. The traditional computer program, it can, yes, determine there are some rule as a sort of program statement, but no, of course, it should be as a vague issues. But when we recognize, we have to recognize such as a very roughly handwritten this character. Which character do you think that this letter, 6 or 0 or the other character? So I can see that this is a Greek character delta, no, sigma, excuse me. Yes. So how computer? So how you can make categorizing the sort of program in the case. Of course, you can document the rule-based program, so one after another. Yeah, here is many rules, possible rules, points, angles, rounds, right into the characters, something like this. So here is a sort of very famous handwritten the letter test. MNIST. This is a very famous mode. So AI or some recognition of the community. This is a very famous test. So there are sort of many image or the pictures or handwritten to the character. So just only focus on the sort of digit from the 0 to 9. Okay, so from the Japanese people, so I'm Japanese. So the letter 4. This is quite different. So when there is a European, so Western European people, so what not characters, read the digit 4. We are thinking that this is a 7 or other better. And the 7 is also a different story. So it's quite difficult to understand, although it's quite difficult to define as a document-based rule, identify whether this character is categorized to be 0 or 9 or 6. This is a big difficulty or the limit the present or the current traditional program-based the computer system. If we do this artificial intelligence synthesis. So now we are going to start get the different approach. We try to emulate or simulate some modules which is already not obtained. So we have some sense of the sensor or the processing information in our brain. So typical mathematical model is linear perceptron. It just categorizes all the certain input to the 0 or 1. That means that is equivalently encoded to the yes or no, or true or false. If we have some input, so output should be this is a correct answer, or this is a correct input, or not correct, wrong input. So if the input and so the internal mechanism is so replaced, or we can change the context of this or to interpret the result. So input is so that just I presented the last slide, so this picture, and the answer is to identify which character 640. So this linear perceptron is mathematical or tool. It is defined by like this. So here is also the red dot line. So the linear perceptron H. So here is also the input X, and the theta is a parameter. So theta is some direction. So like this. So this linear perceptron, so it's identified as two so inputs specified at two categories. So minus or the plus. So H perceptron function, the H returns minus value or the negative value or the positive value. So at the border, so here is a zero value. So we can categorize all these single parameter space to the yes or no. So this is also very simple, but this is also something related to the module we have already in a sort of way. Combine this module, so we are going to emulate or build up a very complicated system as human brain as a system. So probably you have heard of neuron. This is yes, the human brain, very principal, not module. Some cell, the number of is a neuron. It contains in the brain, so it is more than 10,000. Yes, and so each neuron are connected. So like this, probably the synapse. This is the explanation is around 6,000. There's more. So this is like a very complex network. So in 1943, the very famous paper, so Warren McCurran puts. So these three researchers proposed the human brain is sort of a network as by the neuron. So the neuron is connected as a very primitive the device or the unit. So as I told you, the linear perceptron, so it is the possible unit of the function for the neuron as a mathematical or the treatment. So input is the x1, xn, so much inputs or the multiplied vector, and also output is some value. The range is not clear, but also in the case of the perceptrons, minus or the plus. The neuron in the human brain layers structure. So we are going to emulate such a style. So this neuron, this is the module. This should be the layers connected. Of course, the network is very complicated, but the layered structure is easy to start Yeah, the first. Okay, so this a very good summary page for the sort of brain uh, human brain network. So human brain, so our brain, it has a sort of very complex network structure, and so the each unit. So mathematically, so we are going to model by this mathematical function. So in that slide, so the perceptron is a possible one, but also we can choose another appropriate other function. But this network is emulates the human brain. So our goal or the not goal uh, to model or the emulates a neural network at the moment is to develop to realize this very big function. So now here, so we have capital F inputs. We have so many inputs, but this capital F function F to return the output some vector. So if the input is so like this picture of the cat, uh, I'm not sure that this is a picture of a cat. What do you think? It is a possibility. It might be a puma or baby of a lion or baby of a tiger. I'm not sure. But most people answer this is a cat. So this picture should be encoded. The most cases picture is encoded to some 01 binary pixel. And so this is input to the capital F. And so this very complicated compress the function to return its give us some answer of human or the emulated human brain. So to detect so this which animals is should in this picture. So of course the computer simulation, not computer simulation, sorry. So it's a computer mechanism. Yesterday you learn the structure or the hardware structure is very simple. Just only calculates 01 digital. So answer should be also a certain number, a certain series or the bunch of the numbers. So if you have 0.011.0 something like this, that should be the decoding. So if these numbers are the possibility or some probability to the categorization to the already to list the animals. So if this is number 2, the cat, so it is yes. So human brain function F. So it detects the possibility is the highest. So this function, detects this picture is likely to be also the cat. So this mechanism is emulated. So this is an emulation, the current emulation of the human brain by the deep neural. Of course, we have not yet learned the principle of the deep neural network, just only the motivation and some simple idea. Okay, so now, okay, so sorry, we are going to start. So how we gonna emulate the even though this is a very simplest one, but it works to categorize such as the animal photo human dark or the catty or not or like that. Okay, so this is a short break. So the previous slide, I introduced perceptor function. Sorry. This is a very typical so mathematical example. But so we can choose appropriately better the function for there's not only one function to be choose the neuron modeling function. There are many possibilities. So this slide, four functions are presented. These functions are showing some common the property. If the inputs, okay, so here's the Z is the input number. So input is negative or the almost negative infinity. The function returns non positive number, 0 or minus something. In the case of the z equals 0 or z larger than the 0, okay, so in the case of plus or the positive number, the function return the positive number. So we can introduce some neuron function. It returns like also very digital, like also on off or the plus minus. So if the function has such a mathematical property, so we can use such a function as a neuron function. But most cases, so we need to know, or we need to take advantage of its mathematical feature and deep insight already to study or investigate. So these four functions are very investigated very well. So yeah, we utilize these four functions: sigmoid, tangent, hyperbolic. Ryu is the very one, typical one. Just take us zero value if the zero is negative. But it's switched as the count if the number z input z is the larger than 0. So it's return to 0. So this combination of this curve and another line. And the softmap, it's quite difficult to plot on this 2D map. So it is a combination of the multi inputs vector space function. So it is one typical because of its treatment of the derivative. So first derivations is quite easy to calculate. So we use a softmax. Excuse me. Okay, again. No, not again. So let me start. So how we understand we build the network of the layered neural network. So here is the assumption. So we suppose that we have a large number set of a training sample. So we have so many inputs. And so we are going to run the function F. And also, of course, we have some output, but also output should be yes or no. Or, yeah, there is also a teacher training teacher data. We have to compare also this machine return whether the answer is correct or not. So many data are required. So we have, and we can calculate return. This is a value or the vector, the multi-value. Okay, so inputs and the training set. Okay, so now we define the sort of error function. So yes, excuse me, I should. Yes, error function E. So we have the training data set. So if the return data output bar from the neural network, so Y, and the training data T, if this number is the same, this error is there. But of course, so train neural network, so it's not a correct machine or the correct mathematical function to return, identify the new input data to the correspondence to the training data. So E minus training data and that's the Y output value. So there is a gap. So we try to sum up this error, but we have to try to minimize this sum of the error. Of course, the function of the neural function, so it has certain or several the parameter set we can choose. For example, okay, so last slide. Okay, here's the input x1 to xn. And so there are several w1, wm. So these are the habitual or the parameters. So we can choose appropriately as training set and output result. Input data and training data and the output data set. So our purpose to learning the data set is to minimize this error value, to choose or to select the appropriate unknown parameters. So in that size of W is W1 to N. These are parameters to choose. Okay, so this is a sort of very, very analytical or the formula to the error function. So we know the gradient descent method is one possible way to minimize the error function. So if we calculate the descent direction, yes, by the partial differential for the each unknown parameter, and update, or so if you know that's a very advanced way to minimize the unknown function, some searching or strategy is possible to minimize the function. So anyway, we don't have any information, just only have a structure of the neuron function and the unknown parameters. So we try to reduce the error function by this descent direction update So if we calculate this descent direction, so we can update the unknown factor. So like this. So we update multiply the very small factor to the sort of current present the direction. This is a very big very step by step to find out the sort of minimum point. This is a counterplots the sort of LR function. The center point, this here is the minimum, global minimum point. But unfortunately, so L function is not such a very simple structure. There might be many local minimum. So like this. With respect to the local minimum, we should jump to another. So the value. So there are so many techniques to solve such a minimization problem. So okay, so this slide is summarizes how we are going to, we should minimize the layer, so the neural network function. So we apply this gradient, most gradient directions update. This is very simple. But internally, the neural network function, neural function has some very complete formulation. So the partial differential, partial difference, so it is it can be replaced by this formula. So of course we don't have dy over the dwk. So to update the unknown parameters of wk, but y, the partial difference should be calculated by this. So another factor, another function, f dash z or the xk, all these are taken advantage to calculate the descent direction. So one factor that must descend to the direction. So if you choose the sigmoid function, so f dash, so it is easily to calculate by this formula. So we can calculate the descent direction, the element, and then so we update by, if we have input data and the training data, so W is always updates if we have input data, step by step. But no, we only have the output layer to be considered. So internal data is very unclear. So obtain just indirectly populate. So now we are thinking the internal layer and the relation to the output and the input. So these layers are connected. There are several of the unknown factor and the intermediate neural functions. But mathematically, some such a partial differential is calculated by the chain rule. So if you want to calculate this one, so this chain rule is applicable. So this, if we calculate this value, so it is the pass to another layer. the chain rule is so very, very significant so technique, mathematical tool when we update the intermediate layers. There are so many so parameters. So, so this the chain rule is calculated by the so output layer. Of course, the network is input from the input layer to the output layer, so direction. But so this chain rule is calculated from by the direction, the backward direction. So we call this is a back propagation. The chain rule is applied to the output layer, to the intermediate layer, to the input layer. Okay, so this is a schematic. So how the input data and so how we optimize the unknown factor, unknown parameters by the partial division. So this is the input and the intermediate layer, and this is the output. So of course, if we calculate the value of the y, so we input the x from the left to calculate step by step from the left to right. But partial division, so these values are calculate these directions. If we calculate the intermediate layers, so these values are required. This is formulated by these W points here. So this is the unknown parameters, and the delta y. This is a very small derivative of the very small variational value or the error value of this output data. So this is substitute to compute this derivation, partial differential of this function, and this values also. And yes, another partial differential is okay. The formulation like this. So the formulation is very similar, but the components is different. But this is calculated. The start point is the output layer, so it's calculated from output, intermediate, and input layer. So this is start from the right to left. Okay, this is a summary. This is how we build up the very basic structure, just only the one single or intermediate layer of the neural network. So we can update if we have the input data and the training data, so we can update this unknown factor to minimize the error function by this scheme. This is also the forward and the backward scheme. Okay, so please conform yourself to this equation. Yes, this formulation is correct. Afterwards, this. Okay, this is also another schematic. So that is just a summary of a simple case matrix. Okay, so here, I formulate any calculation by the matrix and the vector multiplication. So here, so matrix vector. So yes, so simply deep learning code is generated by the matrix vector multiplication. Or if we have a bunch of data, so input or the intermediate vector is. Yeah, of course, the W is the same. The common numbers are common components. So matrix modification. So deep learning or some AI code is built up by the matrix modification codes. That's why, and also the W and the intermediate, so the vector X and A, they are not required to be accurate. The single precision or the half precision is enough. Just we only have to identify the plus or minus. That's why the precision is required minimally. For example, the half precision, 16 bit. So this is sort of a minimum. Some cases. So AI, so AI-oriented processor of the AI accelerated the GPU. It's installed many accumulators. So it is allowed to accelerate the half precision matrix modification. Yes, I think that you understand some there is a motivation or the essential point when we build this deep learning some application. Of course, this is very principle. So the present current advanced AI code has more or very complicated or very advanced algorithm taking advantage. But anyway, this is the very essential part. Yeah, you should learn or you should remind. This is very important. Okay, so now to go here. So now we like to have a short break to prepare the demonstration of the Python code. Okay, so we are going to have a 10 minutes break, and during the 10 minutes break, please access to the Google your Drive. Probably we don't have any difficulty to access the Google Drive. If you have any difficulty, please write chat, write on the chat. Okay. So we have a 10 minutes break. So we discuss 12 o'clock local time.
Okay. 12, maybe 12:20.
Okay, 12:20.
Yes. Okay.
Okay.
Okay, so we're going back in 10 minutes.
Thank you. Thank you very much. Before we started the session, I got some information from the system administrator. So Ray, Ray Hansen and Amerson, so system administrator, they change the mail address. You can receive the mail to the so another mail address. Yeah. It's time.
野村先生。
Yes. はい。
スライドを持ってない人とかがいるみたいなんですけど、これ、共有ってどうなってるんですか？
共有することになってるはずなんですが、あ、そうなんですか。わかりました。どうしようかな。ズームですよね。だから、ズームだったら、貼り付けられるはずですけども。寺尾さん、持ってますか ?PDF ファイル。
持ってます。
うん。で、ズームのダイレクトメッセージで、全員に対して、ファイルを送るってできるので。
はい。
ただ、スクロールしちゃうともうわけわかんないから。Okay, so, Guy, I've realized you don't, we don't, we don't show today's slides at the moment. So, now Tero-san, so he is preparing this PDF file on the chat channel. So, if it's ready, so please download it from the chat window. Yeah, I'm sorry. So I didn't know that. So you don't have any slide shared. Okay. Okay. So before this session starts, there are so many questions regarding the hands-on prayers. The first half the hands-on experience. So typical one is I don't understand when you show the result and expression, it seems so you use more number execution compared to one precision. So yeah, now this slide is gives you some misunderstanding and honestly to some results. So this time, so it shows us time computation time for the double precision, of course. So this series for the mixed precision. So it says iteration, the first step, second step, third step. The time indicated left hand side. So this is these are the left side. So at the first step, so clock shoulder, so wall clock shoulder 2.2 seconds. So after the second iteration finished, so the clock shoulder 2.3 seconds. So this doesn't mean that the first iteration and the second iteration, each iteration needs this time. So eventually, the required computation time is 2.7 seconds. So you can compare the 3.9 to 2.7. Yeah, this is faster than the double precision. Yes, case. The mixed precision is fast. Okay. So another question. Okay, so I didn't mention there's how to read this mode file. So okay, so first line, so this block, that is a typical result for 48 cores as the defaults as OpenMP running. But so from here, so you see there's one core. Okay, I think there is some indication, two cores, four cores, or something like this. So the block, the results are the parallel results when we use a single core, or two cores, or four cores. So you can compare the parallel efficiency. So when we use just only the one core. So okay, you can compare if we use the whole 48 cores for that precision, just only 3.9 seconds are required to for the value decomposition. But for just only one core, it requires 75 seconds. Yeah, this is more than 20 times requirements for the computational time. Yeah. So there's a parallel efficiency, yeah, or the parallel computing. Yeah, this is a lot powerful. Yeah, you can, yeah, easy to understand. So okay, so if you down screen up the screen down this raw file, so many results yes stored recorded. So please compare the seven results. And then, so other questions? It's just a proof of the concept, I believe. We have problems much larger and heavier computationally. Okay. Yeah, this is really so very heavy.
Recording in progress.
Hands-on URL. Okay, so all right. Now I'm going to demonstrate, and so we are going to share the demonstration code on this Google Collaborator toolkit website. Of course, you can download some Python source code on your PC, or download to our FX server. So of course, front end x86 server is available in the Python. Yes. Okay, so is the material ready to be uploaded? Yes, sure. So please find the 1, 2, 3, 4, 5, several lines. Scroll down. Takeshi Terao is already uploaded. Slide modules PDF is available. Okay, so now the demonstration is based on the handwritten code, so identification. So we are going to demonstrate handwritten code is which number is this handwritten code image. The NIST database, this is a very famous one. So there's a collection of many persons handwritten decimal letters. But you can see here is, so I don't know how many people, so versus example, the handwritten code, handwritten letters from 0 to 9. I don't know which person of which countries. So this database is gathered. So yeah, these are also very, very typical, I think. So character letter 4 and letter 7, letter 9. Yeah, very, yeah, this is very identical. Anyway, so now, so we download the database file to your Google Drive, and we are going to run the sort of Python code to just run the as I explained, the sort of input layer, intermediate layer, and the output layer. Just a very simple neural network module program. So this slide is all these just overview of the structure of the Python scripts. Okay, so when you download the database file from some MNIST, yes, MNIST did your server side many pictures. Yeah, this contains many pictures. Typical example is presented like this. This is probably character the decimal 7, right? But as someone's, it is 1 or something like this. But as in this angle, this must be a 7. So there is a pair, the picture and the input level. So how we can read this letter. So this sets our input to the neural network. So we repeat our learning to modify this unknown the weighted unknown factors until the the values are converged. And then we will input the specific character image to identify neural network which characters, which letters our neural network Python code identify. So we are going to realize the neural network learn the many data. Okay, so this is a sort of very schematic image and the structure of the Python script. So very simple forward just evaluates the error function in the sort of at the backward stage. So we calculate the partial differential for the to update the unknown weighted parameters to minimize the error functions. Okay, so you can look at the NNPI. This NNPI is okay. So you can bring click this link. Here is a example of NNPI neural network Python code. So once you click and access to this URL, so you of course you also start at Google Collaborator, yes, interpreter. But also this Python code is shared by all of the participants. You cannot edit the directory. So please copy this file to your Google Drive to make it editable. Yeah, this is very easy. So choose a file type and save copy in Drive. So this means your own Drive, Google Drive. Okay, so the running the Python code on the Google Collaborator it is just you only have to push the play icon. Yes, at the left upper corner. So push the button, play button. So this script starts calculates. The computational resources are provided as the Google sites. So they provide, this is the voluntary they provide this very, very huge computation resource to the anonymous user. Okay, so I think it takes approximately less than 1 minute to complete the learning phase, and it shows us a 6 characters identification result. But the example 6 letters randomly pick up, so you will see there's another other characters on your Google Collaborators this notebook. So if somebody run the difficulty on running the collaborator or to access the URL to the Google Drive. So please respond or please push your button on the Zoom chat, Zoom screen. No, everybody's okay. Yes, if you already run the this code, but also every time you update this results by pushing the play icon, yeah, the results will randomly select. So the learning place, of course, the learning place is low. The learning training data is also selected randomly. So probably answer might be different at average runtime. Okay, here is somebody is programming download the copy to the Google Drive Python code. Who is this? Google Drive is forwarding to the Python script. Yes. Who is this? Nisha-san, do you have a program to access the Google Drive Python code? Okay, so my Python run has been completed. Okay, Python, okay. Where can I get any link? PZ Santa Cruz. Oh yeah, somebody mentioned this. Yes, collaborators URL. Okay, probably it's easy. Just click the URL. Okay, so if you complete this the handwritten letter example, okay. Yeah, so this example, the results. This is indicating the learning during the learning process. The NNPI, this Python scripts learn the 10,000 characters. So after that, so we pick up the 6 characters and yeah, this Python code is indicates which number they selected the 6 these pictures are categorized. So, but unfortunately, answer. So let go. So it should be 100%. But so left upper corner. So this character, I think most. I think you see that this character should be a 0. That this Python and then PI script, its answer is file name is IBR NN, but some file extensions, it's maybe a different IPNV. Yes. So this answer is wrong, or it might be about 7. Yeah, if this part is unclear, so it might be 7. Yeah, that is might be the reasonable answer. But also in human vision, so this cannot be ignorable part. So this should be 0. So these are so listed. Most of the characters are successfully recognized or identified by the learning process. Okay, this is just an example for the handwritten code. The next step is a more complex picture image. So we try to categorize complex picture. So this is a fashion in this case. Here there are 1, 2, 3, 4, 6 pictures also. Sneaker, boots, and the handbag, and it is sweater, and I don't know, sort of like I bought in the corner maybe a t-shirt or some dress. But anyway, it's going to categorize 10 items from the sort of input different images. Okay, so now we are going to do the more edit the NMPI Python code by yourself. Okay, you can find this. It's several files compressed in a single image file. But please find this line commented out the file access. Oops. Oops. Terao-san, can you hear my voice?
Yes.
I'm not sure about MNIST originals of the handwritten data is so already written in there, so at the top of this the Python script, no, not Python, collaborator script. But MNIST fashion is not described in this. Is it a
そうですね。W レットを追加しないと。
ディレクトリってこれで合ってるのか
な？いや、違います。
Okay. Sorry, this is also so I'll hold we should also like to download this image file from the NIST site after the beginning. I think you can see there. That will get several lines to download the MNIST data file. but so we didn't. Yes, I'm sorry. Yes. Moment. I'm okay. Yes, here. Oh my god. This data is Amazon WS Feminist.
Dr. Imamura,
Yes.
I would like to remind you that this is already 12:10. So in 10 minutes there would be lunchtime. So and then we already still have the quiz, right?
Sorry.
For 15 minutes.
I'm sorry. So we have so many troubles to access the system. So I spend the time. Yeah, that was unexpected.
Yeah. So that's just a gentle reminder. So maybe.
Okay. Okay. So. Okay. So. And next, so closing example. So I expect to modify. You only have to modify this lines, but if you want to, if you also need to download this image data from the data server, so please modify these 4 lines. But now here is some example. Thank you very much, Andrea. If you modify these lines, but it will disappear if you log out here. So thank you very much. And also modify this commented out the lines, so you can run Mr. Fashion program. Anyway, this is okay, almost time. So next version is we don't have enough time to do the demonstrate next version. So please do by yourself. The Google Drive is available any time. So this Google Drive is also available anytime. So I don't erase this source code. Okay, so final page, I should mention is okay. So okay, this page. Okay, so as I explained this, today's example is a very beginning of this deep learning. So explain the example. So this is just a very simple input, intermediate, output layer. But if you want to apply, or if you want to build a more applicable or the practical deep learning code, so please use the others tutorials. So TensorFlow, okay, I pick up all the very nice or the standard, de facto standard software TensorFlow. This is developed by Google. Also, this is also Google. So here there is very rich online manuals and tutorials. Of course, so as you can see, there's some tag or the jump page at the Google Collaborator. So please look at these online materials if you want to apply this or your program, the deep learning. Okay, this is the final page. Thank you very much. I'm really sorry inconvenience time to difficulty and so access to our center. So our supporting team should be run the access from the other countries. Yeah, it's just a very nice experience for me. And I believe so. You had a sort of nice experience to access uh, to our centers or resources. Okay, thank you very much. I'm sorry, so it's almost time for your lunch time, but we should complete the quiz time. Please, I give the button to the MC for
Thank you.
the quiz. I'm sorry to spend a lot of time for unexpected accent.
It's okay. The students also say thank you for you, doctor. In the chat box, you can read one by one. In the meantime, for the students, let's prepare for your quiz. It's on the link. The quiz is on the link here. Okay, here. So it's 15 minutes for the quiz starting from now. Thank you. Okay, the quiz time is over. So this is the end of the module 3 session. We would like to say thank you to Dr. Imamura and Dr. Terao for the assistance for the third module for module 3 this morning. You can also give a round of applause on the reaction button below, ladies and gentlemen. Okay, so we would like you to have a good lunch. Of course, our next session would be invited talk at 2 p.m. It would be great to have you at 2 p.m. sharp here back online. So have a good lunch, and we'll see you very soon. Thank you.
ได้ยินไหมได้ยินไหมได้ยินละ
ได้ Hello again, Ethan.
Hello again. Sorry. Is this Aldo?
Yes.
Sorry, I'm still what is it? My screen is still in the gallery mode, so I'm looking at lots of people here. Okay, how are you, Pa?
I'm
Good
very well.
morning. Good morning there.
I, I was a bit confused by the presentation this morning. A little bit too complicated for me.
Yeah, it was a technical, hands-on technical session, but I think the discussions went very well among the students and lecturer here. I could see some what is it, continued discussions going on as well in the chat box.
Yeah. Over 100 questions. Well, plus all the features, of course. Are you ready? I'm here again. I see that.
I can.
Is Anders already? Hi, Anders. Good morning.
Good morning. Great to be here.
Over to you, Ethan.
Okay, thank you. How are you, Mr. Anders?
Very good, thank you.
Okay, we're just waiting for the all of the students to be admitted in. I think they are almost all of them are here. Okay, so it's a morning time for you there,
Yes, it is.
right?
9 o'clock, so actually you placed it really nicely. Just
Yeah.
had my morning coffee and life's good.
Oh, that's good. Very fresh indeed. Okay, I
Talking about
think
coffee.
yes. Yes, Paulo.
He just
I
got
was talking about coffee. I'll go and fetch one for me.
Yes, prepare your coffee. Always ready in front of you. Also for the students here, I hope you had a good lunch time. Yeah, and ready for the next sessions. Well, long way to go until 6 p.m., but I'm sure you would have very insightful sessions ahead. So, the next one, the distinguished speaker is over here, invited to talk with Mr. Anders Jensen about the Euro HPC joint undertaking. I will introduce and read your bio a little bit, Mr. Jensen. So, ladies and gentlemen, Mr. Anders Jensen started his professional career with 10 years of engineering work developing computing hardware, firmware, and software for embedded systems. He pioneered the IEEE 802.11 wireless network technology in the 90s while working for Symbol Technologies. Anders was instrumental in the spin-off of the Cargolux IT department into CHAM Cargo Systems SA, which became the largest supplier of IT services to the air cargo industry. Mr. Anders was appointed as Executive Director for the European High Performance Computing Joint Undertaking, a joint initiative between the EU, European countries, and private partners to develop a world-class supercomputing ecosystem in Europe with a proposed budget of 8 billion euro. So, ladies and gentlemen, here I present our speaker for today, Mr. Anders Jensen. Please, Mr. Jensen.
Thank you very much. And thank you for the invitation to come here to speak today. I'm really delighted. I think this school is a fantastic initiative, and I think it's one that I hope going forward that Euro HPC will have a relationship with. And as you'll see from my little presentation, what I'm about to talk to you about is a lot easier and a lot lighter than your matrix multiplications of this morning. I'm the break, the extended break after your lunch period before the real stuff starts again after me. So what I'm going to talk to you about is the Euro HPC joint undertaking, what we are, and so there are no programming models, there are no technical, not much at least,
an initiative of the EU, which I would like to explain to you, and how we fit in. So let me just pull up my presentation here. There we go. So, who are we? Well, the joint undertaking, we're an instrument of the European Union. We are what's called a public-private partnership. And what is important for you to know is that the purpose of the joint undertaking is twofold. Our mission is to develop a top-of-the-range supercomputing infrastructure for the European HPC users, meaning I'll go through in details, we are procuring a large number of supercomputers that will be located around Europe for the use of the European HPC users. And as you may also know, some of the EU's different research programs are also open to non-European users. Then in parallel to that, and this is what I think is extremely interesting, the purpose of our little joint undertaking is also to foster the research and innovation within Europe in the HPC domain. So we will not only be procuring computers, but we will also be funding research into various technologies for the HPC ecosystem, that being hardware, software, applications, all of these things, as well as training. And I think this is where initiatives like this school fits in well. There's a very strong focus within the European Union that we are short on HPC skills, and that we need to spread the good word and have more people qualified to program and to manage these machines as they come online. Now, I've already told you we're small, so you'll see there we are currently 15 people within the joint undertaking, which I have to say is the bare minimum to keep this thing running, because remember, it's not just people working with the different hosting entities that's going to host the machines, but it's also a finance team, an HR person, and so on. So I'm very much, I'll talk to you a little later about that. We will be expanding. What is important to also point out is the joint undertaking has existed in its form of autonomous, so operational, since 23rd of September last year. So we're very much a work in progress. And there are a number of things we'll go through where, we're looking forward to being further ahead, but we are working as fast as we can to get there. So I said that it was a public-private partnership. What does that mean? That means that I have the pleasure of having 33 participating countries in our little joint undertaking. So as you may, if you do the math, that's more than just EU countries. We have non-EU countries like Switzerland and Turkey, for instance, that are also participating in the joint undertaking. But also, most importantly, we have private partners. So we have two associations, ETP, HPC, and BDV, Big Data Value Association. They're changing name at the moment. But those two organizations, they base the purpose is that they help the joint undertaking put together our research agenda, and will work with us for many of the research activities. So, mission number one is to procure a number of supercomputers for the European Union or for the participating states. We're going about this, I tell you, I don't think many people have had the pleasure to buy as many supercomputers as I've had the pleasure to do within the space of 3 months. So basically, as we became autonomous, operational in September, I joined as the executive director, and on my desk were a number of contracts that had already been negotiated by the European Commission, ready to go. So I had the pleasure of signing a total of 6 contracts last year and a 7th earlier this year. And in total, we will have 8 supercomputers as part of the current budget. And as you can see there, spread well across Europe. I'll go into a little more details on each of the machines. The relationship between them and the hosting entity. So what happens, as you can see, with 15 people, I'm not going to be running the machines. What the joint undertaking does is it partners with a known supercomputer center. For instance, Barcelona Supercomputer Center, we have Cinica in Italy and the likes, and they will host the machine and operate the machine. The joint undertaking will fund part of the machine and therefore also own part of the computing power. The hosting entity will own the other part, as they are also funding the other part. And that is really the partnership in this. So for the smaller machines, the split is 65. So the joint undertaking is paying 35% of the investments, and the hosting entity the other 65, which also means the joint undertaking will own and manage 35% of the compute time. For the pre-exascale machines, which will be built in Italy, and you already saw presentations of Lumi. We'll have one in Italy, and the governing board has just agreed to relaunch the procurement for the machine in Spain. So I'm really delighted we're moving forward with that. So we'll have the 3 pre-exascales as they were envisaged in the regulation for the joint undertaking. If we go into a little more details about the machine, since after all you guys are techies, so I thought it would only be fair. I'm not going to spend a lot of time on Lumi. You had a fantastic presentation of that yesterday. But we have the Leonardo machine being built by Atos and hosted by Cinica in Italy. I'll of course leave you with the slides, so I'm not going to read the specs out loud. That would take too much time and be completely a waste of time, because you'll have the slides, you can look at them. But what I hope you appreciate as you go through the text is we've taken great care to try and have diversity of the machines. So they're not, of course, there's only so many things you can do, but we've tried to have NVIDIA GPUs, AMD GPUs, different types of CPUs, and so on. And that's really the purpose of the joint undertaking side, is to make as many different configurations available to the European scientists as possible. And amongst the smaller machines, we have Melxina here in Luxembourg, we have Carolina and Vega. And again, you'll see that Atos has built 2 of them, but we also have an HPE machine in the Carolina machine, which is in Czech Republic. Melxina, by the way, I'm delighted to announce, if you haven't seen it, is the greenest machine within the European Union. Something that of course is very important for the joint undertaking, and we'll come back to that. But that was really quite an achievement that it was named on the top 500 as being the greenest one within the European Union. And again, the Discover machine. And then this particular one, the Callion, is one that I find fascinating just because it is a micro-FUCO. We have an AMD partition. Again, we're trying to have as many different architectures available to the European users as possible. The timelines we're working to at the moment, you'll see that we have Vega fully operational. Melixena is in its very final phase of acceptance testing. Carolina and Discover going through the acceptance testing as well. And then we'll have more machines joining later this year and early next year. So I mean, green is key not only to the joint undertaking but to the European Commission and the European Union, and therefore when we've selected the hosting sites for these machines, a key part of it was how the hosting entity what they could offer when it came to energy efficiency. So all of the machines. Not only are all of the machines water-cooled, because that's what we can do in the procurement, and we've looked carefully at how we can tweak the efficiency of the individual machines, but we've also looked carefully at the data centers that will be hosting them. So for instance, again, here in Melixena, here in Luxembourg, the reason that Melixena gets to be named as the greenest machine in the European Union is not just because the machine itself is efficient. It's also because the energy is being provided by a cogeneration plant that is co-located with the data center, and there's a symbiosis between what the cogeneration of the electricity and the excess heat from the data center that forms this very efficient power generation. Equally, you heard Kunio talk about Lumi yesterday. I mean, it is, in all fairness, easier in Finland. You just open the window to cool, but they've done a lot more than that. So we will have, as Kimmo explained, we'll have all the power from hydro, and of course there is a natural cooling advantage. But it's not just in the cold areas. We have a similar story with the data center that's currently being built in Portugal. That care is being taken to make it energy efficient. And I think the problem with these machines is they consume energy, and the more efficient we can make them, the bigger machines we can also afford to run. It's really a win-win to do that. If anyone's sitting out there thinking, so that's all great, the joint undertaking is going to have all of these machines. How do we get access to them? Well, I would invite you to visit our website. Up there, you will find the access policy as it has been agreed by the governing board of the joint undertaking. And there are access modes in which you can apply for access. And as you are aware, many of the European programs are larger than just the European Union. So I would encourage you to have a look to see if something fits. We're still in the early phases of this. As I said, there's only one machine that's really live at the moment, and we are also gonna take this initial phase as learning curve for the access policy to see how and to adjust as we go along. So if any of you are familiar with praise, you will find the access policy relatively similar to what you've seen with the praise way of assigning access. And it is also, we partnered with praise, and we're using them for the evaluations. The actual assignment is with the governing board, who owns the time, but we're using praise to do all the evaluations of this. So it should be familiar to those people who've tried that. Research and innovation, as I said, there's a lot of focus for the JU at the moment on procuring machines, because that's really, the JU was set up because there was in part because it was recognized that there was a shortage of HPC capacity within Europe, and therefore we are catching up with that with these 8 procurements of machines. But the other pillar is very much focused on research and innovation. So while it's been recognized that there's a shortage of compute capacity within the European Union, it's also recognized that within industry and within research, we need to boost the work within HPC. HPC is deemed to be extremely important for the future, and we need to make sure that our European scientists, but also industry, is up to speed and able to compete within this space, so that Europe as a body gets a lift, gets a positive boost in this. And for that purpose, the joint undertaking has a research agenda under its current regulation, where we are supporting a number of initiatives. Again, this is the joint undertaking funding initiatives that are then being run by consortia that have declared an interest in or put in a bid for funding. So you will see we are currently supporting pilots ahead of exascale on how we're going to on how to work with exascale machines going forward. We are getting into quantum. I'll get a little more into that, but that's also already funding work within that. And then very much a flagship for the European Union is what's known as EPI, which is the European Processor Initiative. This has been going on for a while, and the idea there really is for Europe to produce a microprocessor for the purposes of HPC. We are the focus within that work is twofold. We have work on an ARM-based platform, but we're also getting into RISC-V as an ISA. So it's really exciting. I think it's going to be extremely interesting to see where this goes. We're also doing work within software and applications. So I think that's also important. It's not just hardcore technology as hardware. It's also software, the whole stack there the whole software stack for HPC, but also getting into applications and tools. And then finally, there's a great focus on skills and education, training and education. We need more people like yourselves that fully understands how to use this technology and how to take advantage of it. And there's just not enough opportunities at the moment for people to get access to a training like you're having it today. So the aim really is to boost that. We're looking at, right now we have a call that's just closed on getting a master's program for HPC, for instance, within Europe. So that's the initial, all of this is the initial work. Because what's happening is that everything I've spoken about up until now is what was set up for the initial budget. So this was the regulation that has governed the joint undertaking up until now. We are in the very final phase. The European Parliament has voted on the new regulation, and now it should be a formality on when it will come into force. But that takes the joint undertaking to new levels. We will, first of all, we'll do more of the same, which means we'll buy even more capacity. We'll move on to having exascale machines and post-exascale machines, but also more of the smaller platforms, mid-range machines, in order to have, again, diversity of architectures out there and serve different needs. So we'll very much be continuing the work on expanding the infrastructure beyond the initial 8 machines. We will also be investing in interconnectivity, high-speed internet connectivity, and federation of the machines. We will be investing further in the application space, but the other area that we will now get into is going to be quantum computing. The joint undertaking, again, this is a place where, if you look at it at the moment, I think it's fair to say we have yet to really understand what it can potentially bring. But at the moment, a lot of research is being done on private hands within corporations like Google and IBM. The view here is very much we need to make sure that we also, on the public side, are funding research so that everyone has access to these technologies as when we find out what they will be really good at. So there's quite an ambitious program for the JU to get into quantum, fund quantum research, and to join quantum accelerators to the HPC infrastructure. And again, make all of that available via the connectivity that we're setting up, so that any user within any European scientist can get access to this infrastructure. More importantly, from a what should we say, joint undertaking point of view, the new regulation takes us to allows us to hire more people. Currently, I am not allowed to hire more than the 15 we have right now. With the new regulation, we'll be taking that up to between 40 and 50 people over time. So if anyone's sitting out there and thinking this is super cool, then have a look at our website. There will be opportunities coming up. And on a budget side, we are looking at about 7 billion that the joint undertaking will be spending over the duration of the new regulation, which is the next 7 years. So not only are we finishing up, and there's still a lot of work to do to get the current what we've promised to do under the current regulation, which is 1.1 billion euros. But then we will have the next 7 years to expand this further, as it has been stated here by the new regulation. Just for those of you out there, this is where the funding is coming from. So we have a Digital Europe program. We have which will be funding infrastructure and federation. We have a Horizon Europe program, which will be funding technology applications and international cooperation. So again, back to initiatives like this school. I hope that we will have a stronger relationship in the future, or a continued relationship in the future. And under connecting Europe, there we'll see the interconnectivity and so on. Now, as you all did matrix multiplications this morning, math should be one of your stronger points. So if you do the math there, you're quickly going to say, hang on, that does not add up to 7 billion. Well, that's because this is a partnership, as I said, we have 33 participating states. And every time the joint undertaking spends €1, the participating states spends €1. So most of the programs are funded 50-50. So when the governing board chooses to spend money in an area, then the participating states will equally pay. So the governing board choosing to spend money on an exascale machine under the new regulation, well, the joint undertaking, as I told you, will pay 50% of that, and then the consortium that will host the machine will pay the other 50%. And the same thing holds true for research programs. When we fund 50%, then the participating states will fund the other 50%. There are a few exceptions. I mentioned the master skill program. That is something where the governing board has chosen that the joint undertaking will fund that fully. So that gets me to the end of the presentation. I'm very happy to take any questions you may have. You're also very welcome to follow us on our website, on social media, and for that matter, should any of you have a question at any point in time later, you're more than welcome to drop us an email, and we will be very happy to engage with you. So with that, I'll stop my sharing, if I can, and I thank you.
Okay, thank you, Mr. Jensen. So we would like to open questions and answers, right? So ladies and gentlemen, if you have questions, maybe let me check the chat box first. You can also give us the raise hand button, and then we will ask you to unmute your microphone. Okay, there's no questions yet here. Okay. We got one question here from Thailand. Mr. Miss Warawan Diaz Carvalho. Could you please share with us more about the upcoming EU microprocessor for HPC? That's the question. Yes.
So the EPI program, as it's known, European Processor Initiative, has been on its way for a while, and a lot of work has already been done before the joint undertaking. So as part of the European Commission, the ambition has been to create European IP, intellectual property, within the area of microprocessing, and the aim up until now has been very focused on an ARM-based CPU. You can say somewhat piggybacking on the ecosystem that was available there. That work continues, and we have EPI Phase 1. We're just right now negotiating EPI Phase 2. So the ambition really is to create a microprocessor, a component that could be a key part in a future exascale machine. In parallel to that, because you can say we're not blind to the fact that the world is changing, and there's a new kid on the block, the RISC-V. So the program was recently complemented with efforts to also look into RISC-V. Of course, also you can say a little guided by the fact that the ownership of ARM is changing, and I think we need to recognize that one of the maybe I didn't emphasize that enough in my presentation. One of the aims, one of the reasons that the joint undertaking was created was a recognition that Europe was at a risk of not having access to certain technologies. I mean, and this is because of the European reliance on technologies that are not European. Production in Asia and a lot of American IP. I think if we all look back, it was a bit of a different time in the United States at the time when it was decided to set up the joint undertaking. So there was really on the industrial side, we are trying to come back to having European IP, and that's really a driving factor. It's something that we will continue to do. The aim is very much to be able to build an exascale machine with a substantial component, European component in it. We're not looking to replace everything in there, but we're looking to, I mean, the microprocessor being whether ARM or RISC-V in the future, what we need is we need to rebuild the capability to do that within Europe.
Okay, thank you, Mr. Jansen. Okay, I have here Dr. Galiati raising his hand. Would you like to ask or discuss some things? You can unmute your microphone if you're
Yeah, yes, I to unmute. Yeah, Andrew, so first of all, thanks for your presentation. I think it is certainly appreciated by all our student colleagues, and we can see already got an interesting question. My more question is a comment. So they ask about the European Resources Initiative, which of course, is a kind of the flagship on building the ecosystem. But I mean, the European Union first, and now yourself with the EuroSPC joint undertaking are funding several more projects which are not as advanced at EPI, but I mean, the aim is, as Anders was explaining, the aim is to somehow promote the creation of the entire ecosystem. Because if Europe, like any other region in the world, want to have a safe, constant, and independent supply of high performance technology, we need the entire ecosystem. So the processor, of course, is a very important component. And while, of course, it's taking time to build an ARM-based European general purpose processor, given the complexity of the task, we are making faster advances on the accelerators. And EPI has already produced some silicon on RISC-V based accelerators specifically for vector programming. But there are many other projects, in eProcessor, we are trying to design a RISC-V based general purpose processor. And then we are also building an entire ecosystem with other projects like MEEP, which use FPGAs basically to simulate an entire RISC-V system. So RISC-V is coming up very strongly. Of course, it's a long way to go. After all, up to quite some time, at least 10 years, to reach the point where it's now, and it's still not at the maturity that traditional Intel-based or Cray-based platform are. So, is a major effort. It will take quite some time, but I think we're very, very confident we will reach. Maybe if not for the SSK machine, for the post-SSK, definitely. Thank you.
Yeah, thanks for that. That's fantastic clarification, Patricia.
Okay, we have also one of the students here, Mr. Joshua Dizon from the Philippines. Okay, let me see where you are. Okay. You can unmute your microphone and then ask by yourself.
Hello. Hi.
Hi.
Thank you for the talk and for the presentation. It was really informative. I was just wondering, you mentioned that there was a call for applicants for the program. It's something I've been looking at for a long time. But unfortunately, the deadline is up. May I ask when the next call would be?
So you should not feel disillusioned. The deadline for you is not up. The deadline for the consortia to put in, so again, we provide the funding, but I hate to say it, we don't actually do the work. There's going to be a consortia producing this Callibrium for a master's program and the program. So the deadline for consortia to put in their bids on how they wish to run this has just closed. We will be evaluating that over the summer and then awarding it, hopefully, well, still this year, and then starts the process of actually setting it up. So only at that point in time will you have the opportunity to miss the deadline. So there's still time.
Thank you very much.
So good news for you, for all of us here. Another question, another one from the Philippines. I think this is Ruel Cayona. Okay. So would you like to ask in person? You can unmute your microphone.
Sure. Thank you.
Thank you,
Thank you for
sir.
the presentation. Sir, may I know if when is it expected for non-EU researchers to access the computational resources of EU?
So what will happen there? Again, I'll refer you to the access policy. But what will happen is that we will publish calls where you can, where researchers can then respond to, in a similar vein as researchers are responding to Horizon 2020 calls, where you can express what projects you would like to run, and then we evaluate it, and access will be granted to the ones that ranks the highest. So at the end of the day, there again, we're in the early stages, but you should be able to, up on our website, as the computing resources become available, to see those calls being published that you can then apply to.
Okay, thank you very much.
Thank you, Mr. Cayona. Another question in the chat box, Anders. Thank you for the talk. May I know which supercomputing center focuses on bioinformatics analysis, and which research group leads the bioinformatics analysis on these supercomputers?
So that's a really good question. I must admit I do not have a good answer for you at the top of my head. Maybe actually Fabricio is more knowledgeable on that. I do know that one of the things we are going to be, which was an express request, is now for the procurement that we're doing in Barcelona, there will be more focused on that particular area. It's one of the reasons why we're redoing it. But Mauricio, maybe you can be of help.
Yeah, sure, with pleasure. But first of all, bioinformatics, especially propelled by the recent, the ongoing COVID-19 crisis, is high in the agenda of all supercomputer center in Europe, including the one that Anders covered. Clearly, it will be a focus of the next machine at the Barcelona Supercomputer Center, because there we have a computational group for life science, so for bioinformatics, strong or more than 100 scientists, so definitely there will be a strong agenda. But then, outside that, the European Union has been founding what are called Center of Excellence, dedicated on specific scientific sector. One of them is bio, with a specific focus on COVID-19. And one of them, BioExcel, is in fact the subject we will be extensively covered tomorrow. So the European contribution to Tomorrow Life Science Strategy School is essentially centered around the result of the Center of Excellence, BioExcel, which itself extend to several supercomputer centers from, I think, the lead partner is the KTH, Supercomputer Center in Stockholm, but there are many other centers collaborating. I mean, Cineca, Barcelona Supercomputer Center, ULIC, many other centers. So look also not just to the supercomputer per se, but to the Center of Excellence. And in particular, there is BioExcel, and then there is Exascale for COVID, is another interesting Center of Excellence, which, by the way, they are very open to collaboration with people around the world, very much including Asean. And the clear evidence tomorrow, they are doing most of the lecture tomorrow come from BioExcel.
Thanks a lot, Richard. And I do apologize to all of you. I've been in this chair for 9 months, and unfortunately, one of the problems with COVID is I've not been able to go around and actually meet with people and get to know exactly what's going on in each area. So it's great to have people like Fabrizio who's been in this for a lot longer than I have, and with the help there to be able to answer these questions.
Okay. Yes. Well, we hope the pandemic is going to be over very soon.
Can't wait.
Yes, can't wait. I'm sure also these students also can't wait, yeah, to actually making such a good move, yeah, to higher educations and all the fellowship programs such. Yes. Hi, Fabrizio. Now we can see you. Hello. Okay, well, we have another 5 minutes. I think, Anders, would you like to say something, maybe closing the session with another insights?
Well, I think at the end of the day, I want to reiterate that I'm really grateful for the invitation. I think this is a fantastic initiative, and I hope we can continue to work together. I think international cooperation, and maybe that is how to close it. I mean, I don't think it should be misunderstood when the European Union and the joint undertaking has been set up to enhance European IP. That does not mean we don't want to work together. On the contrary, we just also want to enhance what we do in Europe. But international cooperation is a particular pillar within the new regulations. So I think it is just important to emphasize that we're not closing. We're not looking to close up. We're very much looking to work together with all of you. I think there's a significant shortage of skills and knowledge and research within the HPC community or within HPC, and therefore working together is the only way forward. So I think I'll close with that, and thank you very much again for the invitation.
Yes, thank you very much, Anders, and thank you very much, ladies and gentlemen, students, for being, for all the exciting questions. And if you would like to know more or having further questions, you can also email the HPC school, and then we can also forward it to Mr. Jansen here. So before our next session, we have 15 minutes break for the students so that we're, re-energized for the next session and the next quiz. So yes, that being said, thank you so much, Mr. Anders Jansen. And for the students, we're going to see you very soon in 15 minutes. Thank you.
Okay. Thank you very much, everybody. Bye-bye.
Thank you, everyone.
Bye bye. Thank you, Anders. See you.
Yes. Okay. I think most students are still having break now. It's okay. So I would like only to announce that the next one is sent from Professor Labarta, and his slides, his materials already downloadable in this website that I put here, that I put in the chat box. On hbcschool.net, so you can download and prepare yourself before the session starts in 8 minutes. Thank you.
Hello? Hello, can you hear me?
Hi, Fabrizio.
Hello?
Yes,
Yeah.
Fabrizio. Yes, we can hear you.
Yeah, I'm back. Yes, I was gone for a physiological break.
It's okay. We were just announcing to the students that Professor Labarta's PowerPoint can also be downloaded from the website.
Okay, great.
Yes, it's in the chat box. The link is in the chat box if you would like to access it.
Okay. Okay. So let me. I don't seem to have the full control of the mute and the video, so you probably have to do it for me. Okay, now yeah, you can see me, and well, you can hear me. But yes, we're reaching the top of the hour in 5 minutes.
Yes.
So I can. I don't think anything is needed from me anyway. I will mute, and if you.
Okay. Thank you, doctor. Yes, 5 minutes to the next session. So prepare your coffee. I could also see Professor Laberta is here already.
Hello.
Hello, how are you, Professor Laberta?
Good.
Okay.
Ready.
Yeah, we're getting ready there. We're just waiting for some students to come in 5 minutes.
Good.
Okay, thank you.
Good morning, Jesus.
How are you, Fab?
I'm fine.
Good.
Yes, yes. It's
Okay.
the day for me. I've been up from 3 a.m.
Well, I went to bed at 2:30 a.m.
Okay, so okay.
Preparing slides for just work around the clock.
Okay, I think most students are already here now.
Okay, good luck, Jesus.
Thank you.
Okay, so welcome back. Welcome back, class. Welcome back, everyone. Now this is the session for module 4. Yeah. So I believe that you would already be able to access the materials from our website hbcschool.net. If you don't see them yet, just hit the refresh button so you would see it, and then you would be able to download it. Okay, so your next lecturer is here already, Professor Jesus Labarta. How are you, Professor Labarta?
Hello.
Good morning there.
Afternoon. Yeah, good evening.
Yes, good morning. Where are you based at the moment?
I'm in Barcelona. We're
Okay.
yeah, this is my first presentation from the new building. We've moved yesterday to the new building, so
Oh,
that's
very
a
fresh.
nice thing. Yeah, nice place.
Okay, thank you so much. So I'm going to introduce Professor Jesus Labarta with his bio. First, Professor Jesus Labarta has been a full professor of computer architecture at UPC and the director of the Computer Sciences Research Department within the Barcelona Supercomputing Center. Currently, Professor Labarta is the leader of the Performance Optimization and Productivity use of the EU Center of Excellence, where users, both academic and SMEs, from a very wide range of application sectors receive performance assessments and suggestions for code refactoring efforts. He also within the EPI project, the activities, hardware, and software on the RISCV vector accelerator. So full bios of Professor Labarta can be accessed, can be read in our program book. So without any further ado, I would like to give the floor to Professor Jesus Labarta. Please.
Thank you. So let me just 1 second try to share the screen. Can you see it?
Yes, we can see that.
Okay, perfect. Okay, so it's coming. Okay, so I'll be talking for the next 2 hours and a half, something like that, right? About making applications scalable, and kind of my disclaimer when you get to a certain age is you start using the arguments. One thing. About the mouse, I don't see. Well, I guess you can see the mouse. So you can start at a certain age to start using this argument of age before beauty, and I thought it was interesting to there are some concepts which I believe are more important than other visions of the world, and in reality, sometimes I have the feeling that this is well, not what everybody thinks of, but it's what I will be trying to convey to you during this time, that some of these criteria are more important than typical approaches that we have. So this is kind of a disclaimer that this is going to be personal opinions, my view of how parallel programming and how scaling is or should be going. And so it's a personal thing, and it's also a kind of a summary of the message that I would like to give. Okay, so these concepts will be coming throughout the talk. But actually, before starting the talk, I had one kind of doubt or question. I'm not totally sure of the different backgrounds or interests and motivations. So which of these levels of the architecture of system you live in and you are more expert or you are more interested in. And I don't know whether we can organize a small questionnaire if for example, so people who is living or working more at the application, more interested in application and algorithms than on the lower levels of the architecture, maybe can you raise your hand in the participants in the Zoom so that I can have a feeling that about. So I see not that many people on applications. Can I see, so do I have people who has interest on the programming models and the runtimes and the parallel programming models and interest and experience? I'm not seeing many. And on hardware, on pure hardware aspects. So there's more interest on hardware aspects also, which, I mean, that probably could be a topic for another day, because actually my topic today was more about the first middle levels. And my other question, my final question is if you can lower your hand, everybody, and then if ever, the final question would be how many of you know or are familiar about MPI and OpenMP, or have applications or are using applications that are MPI and OpenMP. Okay, that's fine. Looks like there's more people with OpenMP experience or background. Not yet everybody, and I don't know whether I should be addressing much of the basic or the fundamental concepts. Anyhow, I will try to, taking this into account, I will try to adapt. But before that, the first thing is the first kind of message that I wanted to give is kind of this situation in general in life about transitions. Okay, there are things that and if you think not in the plot, but if you think like revolutions or like French revolutions, there are some heads being cut here and there. But the important thing, what I wanted to say, from the situation before to the situation afterwards, there is the important thing are fundamentals that go far beyond what caused the or what was seen during the transition or during the revolution. There's from an agricultural to an industrial war, or from the Middle Ages to focus on God and to focus on the man. So there are changes in transition and changes in mentality, and the fundamental things that are underneath that are far more important than the moments themselves. And what I wanted to say is that we are now, my belief is that we are now in one of phases where we should be migrating from the latency age where we were or we have been, and where our world has been dominated by this need of doing everything very fast, and I want this and I want to get it very fast, which is what has been done, what is happening in computing. It applies at the level of sequential programs. It applies, I want to load the data and I want to load it very fast. Or I want to communicate and I want to send the data very fast, because I wait for that thing to happen and then I go to the next one. This, I would call, this is the latency age. And I think we should start the transition towards what should be more throughput-oriented age, where we specify different amounts of work. We are able to instantiate lots of work, where we say, I want this, and I want that, and I want that, and I want that. And as long as things keep coming, and some of these things I want keep being fulfilled and satisfied and serviced, I'm really satisfied. And the performance of my system is dominated only by or essentially by the availability of resources. And I think this is a change that, as we saw before, there is kind of a change in mentality, which is the important thing underlying what I consider is how to make, and it's the topic of the talk, is how to make applications scalable. I think it's this change of mentality, which is far more important than the specificities of I use this specific part of the programming model of this specific machine or this specific. It's a fundamental longer term type of consideration. So in this context, what I will be talking is about three things which I believe are important to achieve this kind of paradigm switch or this mentality switch, and that are important to achieve this scaling of applications, making applications to scale. The first one is not to fly blind, and in reality, very often I do believe, and again, forget me about this, I'm getting old and saying a lot of my perceptions, but very often I do believe that we do things in HPC, in parallelizing just, let me try this, let me try that, but without really, it's kind of flying blind in the mist, okay? And I think we should not do that. It is extremely important. We should know precisely where we are, how our programs behave, and when I want to get some improvement, get expectations, and why I believe that is going to improve and how much. The second thing is in this trend from latency to throughput is this asynchrony and this capability of overlapping things. And I will be talking about this. It's like in the title is more about order than about overhead. And if you talk, many people today is very obsessed about overheads and minimizing overheads. I do believe that it's more important to be flexible in specifying orders than the overheads. Of course, overheads are important, are fine, but being a flexibility in specifying order is more important. And the final thing that I'll be talking is about malleability. This ability to change the structure of the application, the actual amount of resources that the application is using, be able to change that. And unfortunately, in HPC, in the way people have been programming in the past, this has been very, very rigid. I mean, people have been doing, I want this for this number of, I've prepared my program for this number of cores, and because I know that this core is doing, that static world is gone. So the world is very dynamic, is very, in many respects, dynamically unforeseeable, and what is important is to be able to adapt to it. So I think these three things are very important in order to really scale our applications. Okay, and these are the three main topics I will be talking. So what I have nevertheless is about the HPC platforms and the programming models. It was, I don't know, I mean, not everybody answered that about they were knowledgeable about MPI and OpenMP. Maybe I'm trying to go a very fast shift through what HPC platforms are, and in reality, this is how they are. We have clusters with cores that access a shared memory with a potentially given memory hierarchy, and they connect through some sort of interconnect. And this is the general structure that we have. We may have heterogeneity in this course or not, but this is the high-level view. The actual message I wanted to give is, and by the way, these are characterized by some of these parameters, and people talk a lot, oh, my machine has this many, whatever, bytes per second or whatever. So these are the kind of fundamental characteristics of our machines. How do we program these systems that have these separately distributed memories? So we have programmed them with MPI at the core level, which means out of a problem that I wanted to fix, to solve, I decide how to distribute the data, how to partition the data of the original problem into pieces that I will be allocating to different nodes in the platform, which I will be transforming my sequential program with the things I wanted to do on processing that original data into a program that is run on each of these nodes. And there are some issues that might be needed. There's a need of changing the loop bounds because it's only now everybody affects only its own local data. There may be changes needed into the indexing, all these things is, so some of you mentioned you had experience in MPI. This is what people which is using or has been doing MPI applications has been doing. Okay, actually from time to time also because you need to really communicate, and when you do this communication, you need of course the MPI basic mechanism. So for those of you who have no experience or no knowledge about MPI, maybe through this basic website you can find out about the standard itself. But in reality, this is what happens with MPI programs, and this is this data which actually everybody is using part of the original program. Maybe you need additional local data for intermediate variables that have to do with this communication, but then you release change messages between processes. If you go to the OpenMP, it's kind of within one of the nodes, and within it you had the original program where instead of partitioning the data, you just partition the computations. And now instead of using like here an API to communicate send specific functions that do the send and receive data, you have pragmas that tell you how I want to partition my computation space, my iteration space, and they execute on a shared address space. The typical OpenMP structure is very foreground, is very, I do this loop, go to the sequential part, then I do next loop, then I go to the sequential part, go to the next loop. And so this is very foreground type of parallelism. For those of you who may want to look more about information about OpenMP, you have the website of OpenMP, and this is kind of the basic two programming models that today, and I think for a long time, we will be having as programming models for large parallel machines. On one side, MPI is here to stay. There's a huge amount of codes which are already MPI. OpenMP offers the potential efficiency of fast communication at the internal levels of the within one of the nodes, and hybrid, so it's combining both approaches and trying to get the best of both worlds. In the past, there has been some nevertheless, some negative experiences, and that's why also it's important to really understand and to really know what is the actual behavior of the programs. So this is why the first thing I'm going to talk is about not flying blind and what is it needed, or what is the approach to really understand it. And really the first is we need tools. We need performance analysis tools, and we need the ability to do very deep understanding of the behavior of the programs, not only for developing, but it's even kind of, I have this thing for lawyers, okay, is knowing who to blame. And probably very often we do blame NPI, and maybe the problem is not in NPI. We do blame the vendor of a given thing, and it's very important to know what is the real cause of our problems, because if we know it, we will be able to address it. If we don't, we will be just flying blind. And the other thing I want to vindicate is the role of the performance analyst. Okay, if in the same way that you go to the doctor and is able to interpret magnetic resonances or whatever it is, and tells you what are your issues on how to improve or health your body, I think the performance analyst should be doing that kind of role of being able to analyze and understand displays and being able to give useful, semantically important information to the application developer. The performance analyst is not an expert on the applications, but is an expert in really understanding those displays and doing some sort of, let's say, informed speculation, being able to tell people probably this is what is happening in your system. So what I don't want is to say that the performance analyst has to tell the application developer, this is what happens to your application. So the truth is neither on the side of or on the knowledge, very often on the developer, nor on the side of the analyst. It's a matter of trying to get insight of what is the behavior and trying to understand what we do. And like in many other places, we use computers to really understand matter and understand the universe and understand and we use in a very limited way computers to understand computers. Okay, it's very much like this. Okay, so we very often look at printfs or timers, and we have very limited usage of the machines to really dig down into details of the behavior of the machines themselves. And this is what I would like to to present is the kind of tools that we have been working for many years now, where we believe that we provide a very flexible mechanism to really understand with very detailed behavior of the applications. And the framework is based on an instrumentation package where that captures, you execute the application under this instrumentation package, and you obtain a trace file which captures events of what happened at what time. So for every call, what call was done, how many bytes were sent, to whom, this kind of information is captured into a file. And then what we have is this browser which essentially navigates that data. The framework has many other components. It's possible to do simulations of what would happen if the network had been a little bit faster or much faster. Okay, so this is more functionalities that we have, and we have analytics. If you think of performance data captured by these instrumentation packages, it's like a huge source of data. It's huge, so you can do lots of analytics. I'm not going to talk today about these things, but really is something that is potentially very important. I will be focused on the process of the analysis. I will actually not look much at the process of obtaining the traces. I've given you hints or links to follow if you are interested in doing that on your applications. But I will present the basic fundamental model of analysis. But just a couple of words about what is the trace that Extrai generates out of you run your MPI application or MPI plus OpenMP, and you obtain an ASCII file with timestamped events. Essentially, every row here has a timestamp and has a sequence of events. For every event, says it has a type and a value. The type says, for example, this is an MPI call, and the value would be the number of MPI call. Or this is a hardware counter read, and the value would be how many events of that hardware counter have been. So this is the basic functionality of the trace. Of course, it has information about which threads, which processor. That's the basic information, and these traces can be from tens kilobytes to gigabytes or tens of gigabytes. The idea, we have mechanisms to navigate that data, but the idea is to be able to browse this data and dig down into the information. That is numerical information. If you go, there's an additional complementary file which what does is provides the symbolic translation. So these numbers, what the numbers translate to in terms of functions in the program, or in terms of which specific hardware counter each of those events captures. So what is Paraver? Paraver is just the browser that is able to look at that data, manipulate it, also cut it, filter, but essentially visualize it and present it to the customer. And has a kind of a multispectral philosophy. I'll be talking about it. And it has a mathematical foundation underneath. We happen to use it for performance analysis, but we have users that use it just to visualize, for example, voltages and currents and positions of sensors in industrial machinery, for example. Okay, it's just a browser to visualize a timestamp sequence of events. And when I was talking about this multispectral, is this vision of you look at one reality, and in our case the reality is the trace. In these examples, the reality may be the stars or maybe flowers. But you look at it under different filters and different spectral bands, and you get different informations which are complementary. So this is a little bit the kind of approach that we try to follow. You have one reality, which is one trace, captures what happened in a given run, and you visualize different views that show you different kind of information, and you can correlate those visually. The basic mechanism for the system is like this. So if Actual is going to display views, and these views are going to be essentially timelines, which is a display of a long time, this dimension, and then you have one row per thread, as many rows as threads. So for every thread there is one timeline, the sequence of values that this trend is going through. This display is actually displaying what we call a semantic value, which is a function. Essentially, it's just a function of time. The idea is that out of the original trace, you build a function of time for every process. This function of time is a piecewise constant function of time. So it has a value S1 during T1 seconds, or nanoseconds, S2 during T2 nanoseconds, S3 during T3 nanoseconds. And what this function of time represents is depends on what is the part of the trace that you have been looking at. Out of the event, the trace which had many different events, you actually end up looking at one of those in each of these multispectral bands, let's say. And it has a semantic module which transforms the sequence of events into functions of time. Typical ways is, for example, if I look only at the MPI call events, the semantic transforms those sequence of events into a sequence of values which are 0 if I am not inside an MPI call, and a number, an identifier of the MPI call I may be during the next interval. These functions of time are translated into colors, are rendered into this flat timeline, and you see the timeline evolution of the MPI calls. You can also do the similar thing for a different, in this multispectral, for a different view, for a different information. For example, how long the computations are, or for example, how many cache misses were in a given interval. So the functions of time become number of cache misses during this time, number of cache misses during this time, number of cache misses during this time. So these are the two views, and I will be showing you later a little bit about that. These are the two main views of Paraver, how you visualize timelines and the evolution of the behavior of the application along time. There's another view, which is these tables, which essentially is for each of these views, you can build an associated table. The associated table gets rid of the time dimension, and is a table that has also one row per thread, but has as many columns as different values this function of time had. So you have one column for each of these possible values. So if this function of time was showing MPI calls, you have one column for every MPI call. If this was using useful duration, or this was using cache misses, for example, you would have one column for every cache miss value that you find in this timeline. Well, with cache misses, the value can be so large that put in so many columns, it's really too many. So what we do is histograms, bins. So every column represents a range of duration of the computation, or a range of cache misses, or a range. But in reality, in these views, you have several, one histogram per thread. Okay. So we will be navigating through this. I will be showing you some examples. The important thing is these are the two basic mechanisms. You can go from one to the other and vice versa. And this is what Paraver has. There is this mathematical foundation, which is this process of how you translate the events into functions of time. And here you have ways of operators, many operators that can help you transform these windows of time. And then you have a display of the rendering into colors to try and convey maximum information to the mind of the analysts. These things, this kind of setup of the field of the Paraver in order to generate from the original trace data a kind of view, this is captured in what we call configuration files, which is essentially like a DSL, which actually specifies how to transform the traces by setting up this filter module, the semantic module, and the display module, and generate a view. Okay, so with the distribution and if you will have with Paraver a bunch of configuration files that will be useful to squeeze the information of the trace. The CFGs can also be used by you to, even for cooperative working. You look at one part of the of the timeline behavior, and you say this is an important effect that I think somebody else should look at, and you can save yourself the configuration file, send the trace and the file to somebody else, and he can immediately pop up the same thing that you were seeing. So let me go a little bit into an example of what this multispectral view is. I have here 1, 2, 3, 4, 5 different views of the same reality. This view here, for example, is MPI calls. You see it, you have the name here, is an MPI call. And so the background is outside of MPI, is doing useful computation. So I am in this part where the processes compute locally on their local data. And in the color parts, I am sending or receiving data, and you have the names of the routines. So this gives you a first view of the structure of the application. This other view is how long is the computation, the actual computation region. And we have a coloring encoding, which is a kind of a gradient. And this is, you will see in all the parameter views, you will see light green is a small value. In this case, it's in the order of 1.1 microseconds. Dark blue is in the order of 300 microseconds, I think. So you will be able to see the regions have in the order of 300 microseconds. Somewhere here, there are regions that are in the order of 1 microsecond. So from 300 milliseconds through 1 microsecond, there's a very big dynamic range. So, but this gives you an idea, and you can really zoom in and you can really look at the details if you are interested. This other view is, for example, showing IPC, instructions per cycle. So how fast is the processor executing? And you can see here, for example, this region has, so you can think, so this region, light green, low value has a low IPC. So this region is taking long time, dark blue, long time, because it has poor IPC. This other region, for example, also. There are regions here that are taking short time and they are executing long, high IPC. So you can see for individual regions whether they are long or short, whether it is with good or bad IPC. I have this other view, which is cache misses, for example, good or bad cache misses. And you can start correlating these things. You can start saying, oh, okay, this part has bad IPC because it has a lot of cache misses. And we all have this mental idea that, okay, large cache misses mean bad IPCs. These things are very, very relative. So same values of cache misses may end up, depends on the instruction mix, for example, may end up on better or worse performance of the scalar computation. What this gives you is the possibility of looking at those things and start doing kind of speculations. Yeah, this region has good performance, scalar performance, because it has good locality or not. You can start thinking like that. So the other final view here is about the colors. So this is kind of linking. So we are very focused on the behavioral structure of the programs. What is the behavior along space and time, processors and time. But people also need to know where the things are in the source code in order to correct the possible issues that may be detected. So you have views that show you that kind of mission. Tables. So if we do a table of the MPI calls, the table has one column for every MPI call. This is the standard profiles. The color again represents low value, dark blue means high value. And on every entry of the table, you have a statistic, for example, percentage of time. So what it says is this column, which happens to be outside of MPI, is taking most of the time, and it's true here. Most of the time you are outside of MPI. This is number of calls, for example. This region has more calls, this MPI call has more calls than this other one. Or this is the average duration. This MPI call, which happens to be this one, which is an old wall, happens to take more, the average duration happens to be larger than in the other routine. So what I'm trying to say is you have timeline view, multiple timelines of the same, physically exactly the same part of time and space. The windows are synchronized. You have tables, which are profiles or which are histograms. which actually gives you detailed statistics or the distribution of the given metrics. For example, distribution of what is the duration of the computations or the distribution of what is the IPC. Okay, I'm going to skip this part. So that was up to here. And actually, this is the kind of displays that I think would be interesting for people to look at during, as a performance analyst. I have material here about the internals. I'm not going to go through it. There is an additional information for that in some slides that I provided additionally of all the flexibility that you have in order to compute and derive metrics that show cache miss ratios or that show you name it, message sizes or average bandwidth, everything. You can really squeeze a lot of information out of the trace. So you see, for example, this is the kind of configuration files that are provided by the distribution. You can look at what is the duration of computations, how many MPI calls, what are the message sizes, what is the effective bandwidth that you are achieving, for example, what is your number of instructions, what are your cache miss ratios. So you have the whole of these configuration files, and with the tool, essentially, you load the trace and you then use I want to look at now at cache miss ratio. So you pop up the configuration for cache miss ratio. I want to look at message sizes. You pop up that view. Okay. And this is the place where you can either download and really follow these things, and you will have hands-on tutorials that you can play. You have more presentations that can help you in understanding some of the information. I will be going through some of these topics later, okay? But here you have material in case you want to play. The tutorial provides both the guidelines, provides traces, and you can navigate and browse. There's one thing is navigate with the browser, and then the other thing is to start doing analysis. So I've gone very fast through the views and through the tables. I will be using them during the session, during the 3 hours, and I hope by the end we have a little bit more of a certain ability to understand, to read those plots. But just this kind of the idea is this thing of you have a trace, you generate hypotheses why you get good or bad performances, and you try to validate those hypotheses, and this is kind of the scientific method, where tools are only instruments to help you validate or reject. Okay, so tools are not going to tell you nothing more than just helping you navigate the data and understand the data, and you are the one who really generates the hypothesis and validates it. And it's a very long loop, and the very first steps are, very first iterations are probably easy. Machines in reality are complex things, and when you start digging down and digging down and digging down, things can get very complicated. And it's true, there's one point, there's one moment where one may not be able to find really a hypothesis, and may not be able to validate. But it's important to quantify where that happens and at what level that happens, and acknowledge where is the point behind which we cannot further explain the behavior. But it's true that in reality, in current practice, the community stops very early in this loop, and where we try to push these people to go down deeper into this loop and evaluate much more. The thing is then, this is another recommendation, it's like when you go to the doctor, it's better, if you have a little bit of fever, it's better not to take yourself an antibiotic and then go to the doctor. You first go to the doctor, and the doctor will decide what is the issue. Probably here we try to do, I'm going to do first this change in the code, then this change in the code. It's not a big problem to have a code which is not perfectly performant. It is important to analyze it and really understand the details of what are the issues it has and what are the potentials. Okay, so the tools can help you do that, but still, you have so much data, you have to browse and to navigate and to understand that much data that essentially you can get kind of trapped in a hole of looking at something which ends up being not really that important. So the tool is important. It's important to be able to, but I do think that I actually would not recommend you to start by looking at the details of the trace in terms of trying to quantify the performance. I think we need some top-level abstractions and top-level mechanisms that give us overall understandings of of the behavior of the application. So what I'm going to show is the kind of methodology and that we use, for example, in the Center of Excellence by the European Commission, where we actually do analysis of many codes for many other centers of excellence as well as other industrial or scientific partners. And a little bit the methodology that we use and what we do to try and avoid a little bit is getting trapped into looking at very small issues that really may not be that important from the global point of view. And so this is about the methodology and a model that helps us describe the behavior of the applications. And I think it's the first one. And I will start by comparing to the typical practice. So what people do is you run with 1 core, 10 cores, 100 cores, 1,000 cores, you measure the time, and you paint those scaling plots. And there's this, you can either paint speedups, you can paint efficiencies, but this is what we have. And people tend to argue about the behavior of the application based on plots. So, oh, my communication is killing me, and that's why my actual speedup is not the ideal, and I'm not using efficiently all the processors. That's very typical practice. I think it's important to go a little bit deeper, both in terms of understanding as well as later in terms of detail analysis. So what I want to say is it's not a matter of doing these scaling plots and that's it. There's a real journey in trying to understand the behavior of the applications. And this is the kind of the methodology that we use in this project. And the journey starts by knowing where you are, knowing what your application is. We are analyzing codes from many different sources, from many other centers of excellence. And these codes, I mean, we are not experts on the domain. We have maybe never been exposed to those. And the idea is that the question is, can we identify the structure of the code such that we can really end up making at the end of the whole process may relevant suggestions to the application developer which actually expose a complementary, a different way of looking at the behavior of their program. And in reality, the process is the whole thing is I think is very appreciated by the different centers of excellence, by the different users, because it gives a complementary view. Is just an external view which identifies potential issues. Okay, but the first thing is really there's two communities, and we have to come up to a common kind of overall common understanding of what's the structure of the program. So if you tell me I want to talk about the molecular dynamics code, I know nothing about molecular dynamics. If you tell me a lot of the formulations, I will not be able to understand. So the thing is, can we come to a common language? And the first thing is this identification of the structure, okay? And I will actually just look a little bit of that, which is just understand this space-time behavior of the application, which is curious sometimes, by the way. You could say the application developer knows the structure of the application. Well, with these applications which are 100,000 lines, 200,000 lines of code, some of them written 15, 20 years ago, compiled with sometimes even the developer is really not totally sure or totally aware of what's the structure of the application. So just identifying the structure of the application is a potential first step, which gives a qualitative description of the structure of the application. And how do we get it? How do we do it? We typically do it with use MPI calls and useful duration. So how long is the computation, this gradient kind of metric? and which are the MPI calls. And these are typically useful. It's not that just with this you can really determine the structure of the application. Actually, we are kind of trying to guess that structure. And if you look at this one, for example, looks like, for example, repetitive, right? Looks like some processes take more time than others at every iteration, so it's repetitive, a little bit conceptually, a little bit imbalanced, but always the same type of pattern. And it has these collective MPI calls, these all reduces. So a little bit about the structure of the application. By the way, at the beginning there is something like which might be initializations because it's slightly different. And if we know many applications are like regular computing for many iterations, kind of the same kind of thing. The point is not always exactly always repetitive, and one has to navigate a little bit to try and identify substructure, and it's not always totally. If you zoom, you really see that there may be, for example, in this case, there are groups. This is for 308 processor, 84 processes, and you have groups of 48 that have some kind of repetitive structure, but between them is kind of asynchronous. So it's nevertheless the first stage. The idea of this first stage is to obtain a region which you say this is what I'm going to analyze. It's like, I mean, if you go to Siberia to this and you go extract from the permafrost the mammoth or the tooth of the mammoth, you don't put the mammoth in the sequencer and you want to sequence the mammoth. You take a small part of the tissue and that's what you use for sequencing. Here, that's a little bit the same idea. You have look at the structure of the whole program. You out of the whole program, you identify either a few iterations, either the relevant region, or even small subregions. And you extract a small subregion. That's what you use for the analysis. What do you do with these samples that you use for the analysis? You can visualize them, and remember, this is useful duration, so this shows kind of 3-4 internal iterative structures. You see how it scales when you go from 48 processors to 380, and you can compute, it gets shorter, faster, is what you would expect. It's not ideal. You look at the speed up or the efficiency, and it's not ideal, but it's at least scales something. And then what we have said, this is too coarse grain. The thing is, we could go into a microscopic look at the behavior, and we could get stuck into too many details. Can we have a model, an efficient set of efficiency metrics that characterize the behavior and tell us the fundamental of what is happening with your application? And this is the kind of efficiency model that we use in this POP project, where you say, I have my application has a given global efficiency at the parallel level. Part of that efficiency comes from pure parallel efficiency. So I have all processors active or not. Sometimes they are not, they may not be active. So this is the parallel efficiency. And these are numbers between 0 and 1. So essentially what we end up having is a number between 0 and 1, which says how good is the parallel efficiency. 0 very bad, 1 very good. The global efficiency of 1 would be very good. These numbers, so this parallel efficiency can be probably decomposed into a fundamental thing which determines good parallel, if there is parallelism or not, is load balance. If you don't split your work well between processes, forget, you will not get, you'll have processes waiting from others. So sometimes it's load balance, sometimes it's communication. And in communication, there are two kinds of aspects that impact. One of them is the pure transfer aspect, is data does not go, takes some time. Does not go, even at the speed of light, would take some time, okay? So data transfer takes some time. And then there's another thing, which is dependency change. Sometimes I wait from you, sometimes you wait from me. And in reality, because of this need of communication, we wait from one from the other, but means that we lose time. So the idea is, can we come out with 1, 2, and 3 basic numbers of the tree, which tell us efficiencies, which are absolutely, is this program very sensitive to transfer to the data moon or not? Is this program very sensitive to the load distribution or not? And this is the parallel efficiency part of the model. Then we have another part of the model which has to do with how, when you scale, and this is relative, this is, you take a reference with your reference run, for example, in our case with 48 processes, and the question, is this execution with 96 actually computing, taking the same total amount of computation, split among 96 instead of split among 48, but is the total same total amount of computation? And if that is the case, this would be a good number, but in some cases it happens that you have code replication, and sometimes with 10 processors you do a bit more of work than you would do with only one processor. And these are kind of metrics that are reflected in terms of instruction scalability, for example, representing that with more processors you actually end up doing more work. IPC scalability reflects the fact that with more processors you may be doing that work slower. But it can also be faster. IPC with more processors can also be faster because of locality effects, for example. And frequency, okay, the good old times where the frequency of the processors was static and was known and fixed, those are gone. Now frequency is the frequency that the processor wants, depends on the temperature, depends on. So the question is, when you scale and you run with more cores, it may happen that the processor shrinks the frequency itself, okay? So the question is, these three efficiency numbers will tell you how well the amount of computation scales relative to this original case. So essentially, if you had a timeline where you had a computation in blue and you have the different MPI calls, if you consider all these different MPI calls in different colors, you consider that as non-useful time. The useful time is your computations. If you consider the other ones as non-useful, you end up being able to build and compute the parameters of this model, okay? I'm not going into much of the detail, but you compute the parameters of this model, and that model tells you whether you are very sensitive to load balance, so some guys that do more work than others, or whether you are sensitive to transfer, which is, you would be doing this if this is how the actual run was. What would have happened in an ideal machine? I don't know how much would you pay for an ideal machine, means infinite bandwidth, zero latency. How much would you pay for that? Well, in reality, that will not avoid even these idleness periods, okay? But it will shrink the execution time. How much you gain by that, this is an indication of how sensitive your application is to transfer. And the fact that there are dependencies, that you cannot really advance even more some of these useful computations, blue computations, because there are dependencies, and you need to wait for data coming from somebody else, and you need to preserve the causality of this data. Sender's reception has to be done after sending, cannot be done before. So, but what if you were to break that causality? Then you would have different processes taking different amount of time. And this is a fundamental limit of the parallel efficiency. If there is one process that does more work than the others, no way that you will get perfect efficiency. Okay, so this is how you get the model factors. Essentially, I explained before the other model factors, which are the scaling efficiencies about instruction, IPC, and frequency, which gives you overall how the computation scales. And what we have is, we have program, which actually you feed it with all the 3 different or 4 or 10 different traces, and builds you a table of all these efficiencies, how they scale with core count. For example, this is actually the current output of that program, which is with 48 cores, 96 and 348, 384. How does the IPC or instructions, how does these things scale? And you have to look for, you have low values. So here, for example, for this program, it came out that instruction scalability was poor. Means that when doing 384 processes, it was doing actually larger total number of instructions than 48. So there is a fundamental thing that you have to look in your program to try, if you want to get good performance and you want to scale, you have to try to identify why that. You can look at trends. You can say, for example, my dependencies 97%, 0.97 is good. It gets a little bit worse and gets a little bit worse, and you get a feeling that if you continue scaling, it will get bad. There's another one here, for example, which is luckily IPC gets better. So you keep improving the core count and it gets better. It will not go to infinity like that, but it's probably a good news. So you have to look at trends and you have to look at overall high values. So for example, some of the metrics are can get above 100%, above 1, because really are relative to a reference, and it means that this system is better in IPC than this other system, or in total computation scalability. So what is the result? The result is you have a model which helps you describe at the very core granularity level, helps you describe the behavior of the system, but whose next level of causes, which becomes complex. So you can have load imbalance for many different reasons. You can have serialization for many different reasons. Some of those are instructions counts, uneven distribution of instructions. Some of those may be operating system noise. Some of those can be NUMA characteristics of the machines. Some of those can be overhead of the runtime. So, and each of these things that do happen in the machines can impact or reflect the different metrics. So the metrics is a good thing that helps you to describe overall, and this is what we use in this analysis of this center of excellence code. Is transversal. It's this language is kind of independent of the domain, and it's a way of you can compare applications from very different domains. Okay. And when you then drill down into the actual causes, the thing can be a little bit more complicated, the actual causes. But it's necessary to do so. Our methodology, essentially, the idea is to do the generic steps first, and then it comes to the point where you really need the detailed analysis. You identify here which are the features, the things, the behaviors that are more important and are harming more your global efficiency, and you have to try and find the actual causes for those things. I have here a slide, for example, about what if your problem is load balance. Okay. Well, load balance has one thing, which is some guys taking more time than others. This situation where this guy takes significantly more time than the average, this is very bad in terms of load balance. One guy taking less time than the others, even if it's comparable in terms of the amount of time that is less, this is not very harmful. Why? Because here, all of these guys have to wait. In this case, it's only one that has to wait. When you have load imbalance, you have other kind of complementary metrics, try to find the reasons. So in the same way that we have defined a load balance in terms of total amount of computation, you can define the instruction load imbalance. And sometimes load imbalance comes from a difference, everybody executing different instructions, but sometimes load imbalance comes from everybody having different IPC, different localities, same instructions but different IPC, or running on processors with different frequencies. So one has to drill down into what is the actual cause in our specific case. If you had transfer, for example, for transfer, let me go on the causes. Why is transfer bad? Transfer was computed by comparing the actual run compared to an ideal run. What would have happened in a machine with infinite bandwidth? And in this case, the difference is very notorious. It's kind of for 20 or 30, 40% only if the machine was ideal. But what the transfer efficiency gives us is the comparison between these two things. What we have is we have the possibility of doing many more studies on a simulator about what would happen if latency was 2 microseconds, what would happen if latency was 20 microseconds, what would happen if bandwidth was 1 gigabyte, what if it was 100 megabytes. And by doing these simulations and comparing them, you get an understanding, a feeling of where in the trace do the problems appear, because the problems with transfer may not be all over the trace, they may be concentrated in specific sub-regions. you get a feeling of where these problems appear and a little bit how important they can be. You can do this kind of what if simulation analysis with these tools, where you can say, well, if the machine was ideal, this is the behavior. If the machine had 1 gigabyte per second, it would be a little bit longer. With 500 megabytes per second, a little bit longer. Suddenly, it comes out that with 100 megabytes per second, it gets much longer. So this was, for example, one version of the code. There was another version of the code which was less sensitive to transfer. So you can really get a feeling of how sensitive your programs are to transfer. How would they run on ideal machines? How is important is for you to really try on different machines. Okay. So essentially, for serialization, you have to do a similar study of looking at the actual behavior of the communication and actual cyclic dependency chains. This is what you have to look for serialization. And if you are not able to separate serialization and transfer, because for doing that you require this simulation of under ideal circumstances, and you may not have it, or not all of the tools in the project have that. So you can really still go to the traditional looking at what is the granularity of your applications, what is the message sizes that you are using. One of the things I would try to push you is try to delay as much as possible going towards looking at the profile of MPI. MPI is like a gas, fills whatever space you give it. It's not guilty in many cases of taking a significant fraction of time. Okay, so this is, I think, an important observation. So the same thing you can do with instruction scalability. And so what I'm trying to say is I'm probably going to stop here for 5 minutes break. The idea is up to here I kind of presented a little bit the fact that tools let you do very detailed, very precise analysis. That nevertheless a top-down methodology is very important so that you get an overall view of what are the fundamental characteristics of the application. And after that overall view, you can dig down into the details. And once you have understood the details, you can really start trying to address the actual causes of the problem. So let's do one thing, which is let's stop for 5 minutes. We start in 5 minutes again with the second part, which will be now talking about asynchrony and overlap and how they can be used to try to scale applications when going to large scales. Okay. I don't know if there is any question in this time. Let's stop for 5 minutes now.
Okay. Professor Roberta, there are some questions already in the chat box.
Okay.
Okay. Let me read this for you. Okay. Unless the students here want to unmute their microphone, maybe I would like to Miss Romrawin. Oh, sorry, not Miss Romrawin. Mr. Andrea Alizal. He has a question for you. Would you like to
How do you get the private trace, right? Okay, the private trace. So we have this extrae package, and in the additional slides we have some examples about it. So the extrae is a tracing package, which essentially you have to run your application the same way you do it. You put you prepend it with you do an ND preload. You prepend it with a file to activate the tracing. But essentially requires just modifying your submission script very minimal. In the additional information that I gave you, you have the examples. Okay. And these runs will obtain the parameter trace. Does not need to recompile the application. Does not need, you can have binaries and you can still obtain the trace, right? So no, it can be very often we do this analysis blindly. We don't have the source code. We don't have even actually when I said the trace separates between the numerical trace, the .prv, and the symbolic trace file, the .pcf. is because we had some customers that we had some kind of paranoid. They didn't want us to know the names of the routines. They didn't want us to know anything. So they would give us the numerical trace, but not the symbolic trace. We will be able to say routine 27 has this problem, but we wouldn't even know what routine 27 was. Okay. So what it means, it can naturally be done with really binaries, production binaries. So there's another question about compare time spent in computation versus time spent in communication. I think this is what we have presented in the model. Yes, and I really want to highlight again. Time spent in MPI is not time spent in communication. Okay, it's time you spend time in MPI when you have imbalance, and you should not go and blame the vendor or your MPI is very bad if that time in MPI comes from imbalance in the computations. And so that's why it's important to know the real cause. So this next question is kind of the same thing. So it's the same thing. The model that I've described and the methodology, the last part of the step do this. They tell you how much you spend on computation, which is the parallel efficiency, how much you spend on transfer, on actual transfer, not on MPI, but on actual transfer, limited by the characteristics of the machine and also of the overheads of MPI. And so this is separated that way. Yes, so you have your MPI program. It does it for MPI, does it for MPI plus OpenMP programs. You have your MPI program. You have to trace it. So the question is, does Paraverse generate efficiency metrics for parallel programs? Okay, is you have, yeah, they have to be MPI plus OpenMP. We have also traces for CUDA. We can also trace CUDA. We can also trace other models. Okay, but yes, you have to trace it, and this there's a tool that will generate those numbers. Can we analyze containerized applications? Yes, we have been running. We have not had so much experience on that, so many users, but yes, there have been applications which have been containerized and have been analyzed. Can be used with AI frameworks. Yes, we are using it to analyze some of the AI frameworks. It's a little bit cumbersome because very often they may become I don't know, linked with MKL. Okay, and MKL has not been compiled with -G, so we don't have symbolic information. We can see the behavior, but we cannot really tell exactly which routine it is. But yes, we have examples of people who has been locally and has been analyzing, for example, PyTorch and trying to analyze and understand, well, the impact of the batch sizes, the impact of, so yes, that has been done. Correct. The tool has to be included in the container, but it can. About CUDA. So we have instrumentation about CUDA also. CUDA is a little bit like, so it's a typical application is MPI plus something. It's MPI plus OpenMP. It's MPI plus CUDA. And we can apply to applications which are MPI plus CUDA the models that we have been described, and they will tell you exactly the same kind of information: how much load balance, how much. The only thing with CUDA to me, and all these many of these accelerator things, what they essentially are is that in the computation part that we explain, like a long dark blue region with a long computation, the only thing is that it's a device that does that fast. Okay, so instead of being long things, will be shorter. We do capture information about data transfers and this kind of thing, so you can really drill down into the behavior of that. It's probably not as detailed or as elaborate as the NVIDIA tools, for example, for that, but it gives you on a very large kind of very large scale, you can really look at it, and yeah, it's possible. Okay. So I think we are already past the time. I think I'm going to continue a little bit talking about and these things which I believe are going to be very, very important, which is introduce asynchrony and overlap. And it's something new? No, it's not new. People have been trying to do this for a long time. It's probably sometimes is kind of I want to get rid of this feeling people may have. Oh, I want to overlap communication and computation. I substitute my sense received by I sense I receive in immediate non-blocking calls, and I'm done. And it's not exactly like that. So what I want to show you some examples of these possible things, and just I want to highlight this other message, the thing that there's a difference between our mental models, how we think the machines behave, and how they really behave. So that, and just to motivate that, it's really important to look at the traces to really understand how they behave and really be ready for the unexpected. Machines can behave in very strange ways. And so I'll be showing some examples of these patterns of overhead overlap and synchronization, and I will be talking what I believe would be the kind of right approach to look at programs in the future, and is a bit more of think of potentials and try to be flexible in specifying orders. And I will start by let's take this very simple example. Okay, it's like what we did at the beginning. You do a compute and you communicate, and you have point-to-point communication, sending, receiving data from your neighbors maybe. And I've mimicked this kind of a barrier operation, which does a global synchronization. I mean, in an real algorithm, might be a collecting order, going or reduce, or might be to check convergence, for example, might be different. But this is kind of mimicking the fact that within an iteration you do compute, communicate, and synchronize. And I actually have two versions of it. One of them is you synchronize every iteration, or you synchronize at the end of a whole bunch of iterations. What is the behavior of those things? And maybe you can, I don't know if it's easy to read or not. You have the synchronized case, which is the very first one. You have this behavior. For a round which was, I have the colors, this is useful duration, so, and the colors were between 0 and 450, so the dark blue things are 450 microseconds. There are some orange things, you see them, there are some of these orange, is that they are above 450 microseconds. And even if my program was compute for a given granularity, this kind of internal variable just to mimic a certain amount of computation, even if you have that, you see that there is variability. There are some regions that are longer than the 450 microseconds, which is the average. In this situation, you see the behavior is you do the computation, the dark blue region, everybody does the computation, and you enter into the communication. And after the communication, you have a barrier. Then you go back to compute. In this case, you actually do compute, communicate. You only wait from your near neighbors, and it's just this other kind of pattern results. The thing is much more shaky. Some small delays that may appear, and you see that these delays appear in different parts, and this is noise. So some of these delays, which here are paid by a body because of the barrier, and you don't start again the computation because of the barrier, and everybody feels the pain. Okay, in this case, because there's no barrier, people can go to the next iteration and can compute. And then you understand that some iterations accelerate, some other get delayed. At the end, at the end of the program, you have to wait for the final result. You have to wait for the barrier. Okay, but you get that this kind of asynchrony, and this would be one of the first messages, is try to avoid this global collective operation synchronizing within fine-grained computation. 400 microseconds starts being a little bit fine-grained. Try to avoid it, because it comes out that many of the systems do have operating system noise, which is sporadically, some of the executions get elongated by a few tens of microseconds or hundreds of microseconds. And this on a system where you run with 5 processes, has no impact. If you run with 1,000 or 10,000 processes, you are guaranteed that every iteration, one of the 10,000 will feel this pain, and this pain will propagate to everybody else. You can apply the model to these things, and you can look at the internals of this in an abstract way, of the internals of this behavior. And for example, you can see that the load balance is pretty similar. The code is the same. It's the very same, but it came out that it was executed twice, there's variability, and the load balance started being with this plus 1% of difference, okay? If you look at transfer is 5-6% better, so that's good. And that's inherent to this lack of synchronization and the fact that you allow to really overlap, to really start the next computation without waiting for the synchronization. Okay, you have other effects, for example, IPC scalability. So it gets a little bit better, 5%. Okay, so what I'm trying to say is that, and by the way, this load balance is 94%, so you lose kind of 5-6% of efficiency. And if you look at, if you look at the load balance in terms of instructions that we mentioned is 0.99. So everybody does the same amount of work. The thing is that the same amount of work does not always take the same amount of time. And this is because of noise, this is of many other things, and this is the kind of behaviors that we observe. Actually, I have here a histogram for this observation. This is a histogram of the useful durations. Remember that in these tables, in these histograms, you expect to have vertical lines, which is that everybody has the spike of the histogram in the same place, and this one is a little bit to the left. They are in the same scale, so it means that the spike of the histogram here is a little bit to the left. This is a histogram of useful duration, put here, which means the duration of the computations here is a little bit shorter than the duration of the computations here, which has also some spread, some scatter. And if you look at the zoom region here, you see similar. What I'm trying to say is there are many effects, the effects that may include, for example, on this impact of getting a little bit better of IPC. The fact is that here, when everybody's computing, everybody's computing. When everybody's doing loads and stores, everybody's doing loads and stores. Then when everybody does MPI, everybody does MPI. In these situations, that gets much more. Sometimes one of the processes in the same node, some of these processes do computation, the others do MPI. And the result is that you end up having a more balanced use of the, for example, memory bandwidth. Well, the impact of granularity, of course, this is something which can be a very significant impact at very fine granularity. If the granularity is very coarse, the impact will be much less, and these shaky forms are much less important. What I'm trying to say is that it's good to know the actual case that you have, the actual use case that you have. Another example, this is the other topic. So this is the fact of overlapping communication and computation. What people does to overlap communication and computation. You have your computation. Well, what the people does for overlapping is to do the computation, to use immediate communication requests before. So saying, I want to send that to this other process. You do a computation, of course, should not be dependent on the data that you are communicating, and then you wait for the communication. The original, the traditional approach is I do the communication, so I want to communicate and I wait for the communication to be done, and then I compute. These are the two ways of trying to overlap. What is the result of these attempts of trying to overlap of communications by the application? What is the result? This is the kind of result that I had for this example. So this is the same, this is the 20 iterations, this is the same 20 iterations. Blocking is when I don't attempt to overlap this case. Non-blocking is when I do attempt to overlap. What is the impact? I would have expected more. Okay, I did this refactoring of the code because I thought I was going, by the way, here, if I don't overlap it, I have computations which are in this order of 600 microseconds, but then I have these white things, so non-computation, these are MPIs, And in these MPIs, I have a lot of, so I have a significant amount of time in the communication. So I did the refactoring to try and overlap because I wanted to avoid these white holes here. The result didn't really get it. And in reality, this is one thing which is important, is these things you must have inside MPI a progression engine that actually makes sure that while you are in computation, all the actual protocols of data communication are active and are taking place. This is in most of the implementations doing only when you call MPIs, only, which means that if instead of calling MPI, you just tell MPI I would like to communicate, but you go and you do the computation, you have taken the control out of MPI. MPI is not doing the data transfer. The result is the data transfer is done at the end when you do the weights. Okay, this is in one situation where the difference between what you get and what you expected can be important. Okay, I had other examples here, which this one was with the barrier inside. This is with the barrier outside. So it's a combination of the overlap and the combination with the synchronizations, and you can see that with the barrier outside you have this kind of this wavy type of behavior, but still you have significant fraction of idle time, the background thing, which is not useful, not computing, so it's in MPI. There is a little bit of gain, but it's not an impressive gain. Okay, so I have the numbers, you can look at those. Essentially what I'm trying to say is that it is important, but it may be a little bit a surprise. And in reality, if we claim, okay, I'm not really achieving a real overlap of communication and computation because of the argument I said. When I enter into the compute, I'm not making MPI to progress. So what do systems have? Systems have this, for example, environment variable that tells you, say, I'm going to have in the internals of my implementation, I'm going to put a progression thread that will be taking care while you compute, will be taking care of sending the protocol messages, receiving the data, so doing those kind of things. What is the result? It's a little bit deceiving sometimes, right? It's actually even worse. In some cases, it's actually even worse than the original. So this was the original run. This is how it came. In some cases, you do get a little bit of gain. Okay, you do get a little bit, but not that impressive, and really not totally. So you have more other cases. Depends on the granularity. This was with coarse granularity. This is with finer granularity of the computations, and can be a bit more of pain. And in reality, actually, it can be a lot of pain. I'm showing here only the computations, the useful computations, but I'm not showing in this program. I did put several barriers after this, and some several collective operations after these computations. And you see these collective operations were taking a lot more time in the system with a progression thread enabled than in the system without a progression thread enabled. The message essentially is those things are important. They have other, but they can be. One has to understand them and look at them, because these effects may happen in certain parts of the program, but not in others. Okay, the message is they can be important. There can be a mismatch between our mental models and the reality, but we have to analyze it. We have to look at it. Okay. So, and these kind of things have been used by people for many years, with probably, in many cases, not the expected behaviors, in many cases, keeping those refactorings in the source code, this thing of splitting communications, because this is what eSense do. You split the communication, send and receive, you split that into I want to send, or I send, or I receive, and the wait for the data. You split it. The question in those cases, which actually kind of may make the codes a little bit difficult to read, to maintain, is when you split into I want to send or I want to receive, and I wait for the receive. Ideally, you want to do the iSense, the issues of the operations. I want to send and receive very early in your code, and you want to put the weights very late. But this, what early and late and what is the right place is something that is very dependent on the behavior of the problem answer. And there's a very big question of where is best. Where is a place where this we can really benefit from that? And this question can be a difficult one, can make the codes to look not as elegant as the or as clean as the blocking original blocking codes, and it's a challenge also because the best place is maybe time dependent. Maybe during part of the executions might be better to advance a lot the sense. During parts of the application executions maybe not necessary to advance that much. So essentially, what I would like is, I think it's important to do this analysis of the details of what I am experiencing in my code, and so for this will be reported in the metric with bad transfer, okay? But the thing is, this bad transfer, I want to, in the next levels of understanding, I want to look at what are the actual potentials of achieving that overlap. And the second thing that is very important is, in order to do that, what is the effort I have to spend? How much do I have to devote to refactor my code? I have to split it and put things, start moving things in my syntactic tree. Will that be productive? Will that be resulting in codes that are easy to maintain, for example? And this is an important challenge. What to conclude this section on this asynchrony is an example of how what I think would be important or interesting approaches or the desirable approaches, okay? And I'm going to use this example. Here you have a trace, which is a trace of a weather code, which had chemical transport, I don't know. Essentially, the trace included, and this I have not shown before, included information about entry and exit on routines. So there was a routine, and this is the part of that you spend inside that routine, this purple routine. Then you had a green routine, which this view shows the routines, but when you are outside of MPI. So if it's black, if it's background black, is because you are in MPI. If it's a dense color, it's because you are computing in user level code. So what we have is you are computing, then you enter a green routine, which for some reason has some very fine granularity, and that's MPI compute that with very fine granularity, so significant amount of MPI. Then you have this pink routine, which does compute, again a brown routine that does again communication, again a green. So the question is, how do we interpret, and by the way, sorry, the efficiency in this parse is very poor, it's a lot of time in MPI, okay? How do we interpret it? What is going on? And the question is, we could interpret it this way. So there is, as a dependency, the idea is to interpret the world in terms of tasks, in terms of computations to be done, and what are the dependencies between those computations. And this is, the interpretation is for every process, has to do a long purple computation, and when this purple computation is done, probably there is a sequence of green, pink, brown, green, prick, brown, green, pink, so, and these sequences can be done. Okay, internally, the green depends, the pink depends on the green, the brown depends on the red. But this is done sequentially, so it may be actually that this green depends on this brown. So really, you have to execute the four of them one after the other before you can start with the gray. And the question is, and what I would think would be important is try to speculate about, is it really totally necessary to execute the full purple before executing any of the greens? Maybe yes, maybe not. So maybe this is a question, as an analyst, I can really not know. I can suspect, but I can really not know. But I can ask the developer, and the developer probably tell me, well, in reality, this is what happens. So in reality, out of this total purple thing, there are, in the first part of it, compute something that is going to be used by the first chain of communication activities. The second part is something that is going to be used by the second set of communications. What would be the potential of this? If we are told that this is the case, what would be the potential of this? it would be interesting to change the order of execution such that we execute this and nothing can be. So we execute this, but after executing this, when we can start executing that, we can also execute other part. So we can start this thing before finalizing these other parts. So we can actually overlap this thing here, which happens to have a not very good behavior because happens to have a lot of black, a lot of MPI communication. We can overlap this thing with that thing. Okay. So we start thinking of potentials. There may be many other potentials we may think. Okay. It might be possible that this thing that we go after the brown, the green again. Maybe they are one after the other because they have to do in one specific order, but there is no real dependence. There is no real dependence, so they are totally independent. Or maybe there is one dependence which is caused because of these things are MPI sense, and MPI forces you to execute things, do the sense in order. Maybe, but the thing is, we can think of potentials of how things could be reordered. If you have this graph, if the actual dependencies were like this, it actually means that everything here could be executed in order. You could actually execute this thing before this other thing. Any order, any possible order would be a valid order. So it's important, I think it's very important to try and understand this, which is a fundamental characteristics of the program. Of course, now, if I want to leverage this potential additional concurrency of my program, which can help me fill these holes here with activities from here, it's important for me to know how do I have to refactor to modify the code. Maybe these things are difficult, and this is what I was saying before, and because it requires a lot of refactoring. And in MPI, the traditional non-blocking communication may be difficult because these things may be different routines, and it starts meaning that I want to move code from between routines, and this can be a little bit of a nightmare in terms of refactoring the source code. So the question is, do we have mechanisms to be able to reorder things in terms of execution order, but not reorder them in terms of syntactic execution order? So not defining all of the source code, but still resulting in very different execution orders and possibilities of overlap between this thing and this thing. Okay, this is the kind of approach where I would like to push you to think when you look at what to do, how to improve the scaling of your codes. It's actually is something that you need to look for this syntactic structure to tell you is still. Not everything is, from my point of view, not everything is totally fixed. Not all that I will be talking after this about programming models, but some of these possibilities still are not totally enabled currently by the current standard. But it's an interesting opportunity and need for actually improving the features and the functionalities of the runtimes and of the programming models. But that's how I think things should be done, and of course should be continued. Is the green is this gray thing really needing everything else, or maybe needs only one of them or two of them? And you can think that there's still a lot of potential to identify potential parallelism. The point is then is more a matter of mindset, a matter of thinking about possibilities, potential orders, okay, rather than actually specifying a specific this thing has to be done first, this other thing has to do second, because also machines can, as we said, there's noise, there's variability, they may end up executing slowing parts. So the idea is, can we think of potentials and do we have, by the way, this thinking of potentials is a global thinking, okay? I want to, this may be parallel with that and with that. So this is a global thinking, but then you have to write the program. And when you write the program, you really have to specify precisely which are the orders that are valid orders and which are the orders that are not valid orders. And it's very important to have a syntax that allows us to do this refactoring and with minimal changes in the syntax enables a very wide range of changes in the in the order of execution of this. Okay. So this was this statement: order before overhead. Overhead is important. Okay. Yes, but I push you to think first in order, and of course take into account overhead afterwards, but first think in potential orders. And I mean, I've been given, actually, if you do these kind of things, I've been surprised many times. I did write a program thinking it was with these approaches, thinking it was going to execute in one way. I look at the traces and it ended up executing in a way which I never thought of, happened to be even better than what I had thought of. So it's kind of a mentality that I'm trying to push. So that was about the generic approach. The idea is about what I think are the features in this in programming models that will allow us to do this kind of with minimal syntax modifications, try to change huge flexibility, get huge flexibility in the order of execution. So this is another kind of activities that we've been researching for a long time, which is programming models, which task-based programming models, and we have something we call stars. We have a different whole family of them, which are sequential programming models. So you have the right sequential programs. You annotate them with directionality clauses, and they happen to execute in parallel. And ONS OpenMP Superscalar, let's say, is kind of one of those developments that we've been doing, where we have been actually trying to push features and things into OpenMP in the different versions. And OpenMP has now a lot of these features, and so essentially we keep trying our developments with Nanos, but trying to contribute to OpenMP some features that can help you write this kind of without really restructuring the whole routines, and the whole just allows for you to do a lot of reordering of the execution. And the basics of this approach is to use pragmas that specify for the task, for the spawn. They let you spawn tasks, instantiate tasks, but specify for those tasks what is the data that they use, what is the data that they read, what is the data that they write. With this information, with this single mechanism, the runtime can build dependency graphs. And even if your program was a sequential program, which had a sequential order, which is the default fallback order, the runtime can detect the dependency graph and can schedule the execution out of order, and can there's a main program that keeps instantiating tasks and putting them in the graph, and there are worker threads that keep going through the graph and saying what is available, what is free of dependencies, and I keep executing it. So this is the kind of philosophy which actually has made some of it into OpenMP, and in OpenMP, if you look at the OpenMP specifications, you will see the mechanisms and the syntax, how the syntax in OpenMP is different, of course, from the syntax we have in OMS, but the semantics, the fundamentals are pretty much the same. And you have the possibility of spawning, instantiating tasks. You have task loops, for example, which are useful to say this loop split it into several tasks with this granularity, for example. And you can have nesting. There's a first level of instantiating a single task. Inside it, you can